Mercury is the nearest planet to the Sun, and is the eighth smallest and least massive in the solar system. Due to its proximity to the Sun and its small size, Mercury is the most elusive planet, visible only without optical assistance. It is never visible while the sky is entirely black, as its rising or setting transpires within 2 hours of the Sun. The Sumerian civilization identified Mercury roughly 5,000 years ago, despite the difficulties in observation. In classical Greece, it was designated as Apollo when it emerged as a morning star just before daybreak, and as Hermes, the Greek equivalent of the Roman god Mercury, when it shone as an evening star immediately following sunset. Hermes, the quick messenger of the gods, imparts his name to the planet, perhaps owing to its rapid motion relative to other celestial entities. In recent epochs, many celestial observers have lived their entire lifetimes without observing Mercury. Nicholas Copernicus, celebrated for his 16th century heliocentric model detailing the proximity of Mercury and Venus to the Sun, allegedly voiced a deathbed regret for never having physically witnessed the planet Mercury. Until the latter half of the 20th century, Mercury was one of the least understood planets. And even now, the scarcity of information about it leaves many key problems unanswered. The length of its day was determined only in the 1960s, and despite the flybys conducted by the Mariner 10 and Messenger missions, a significant portion of its surface remains uncharted. The seen hemisphere of the planet initially resembles the cratered terrain of the Moon, a notion reinforced by the comparable sizes of the two celestial bodies. Mercury has a markedly higher density, with a metallic core comprising around 42% of its volume, compared to 4% for the Moon and 16% for Earth. Moreover, Mercury's surface markedly contrasts with that of the Moon. For instance, it lacks the extensive dark lava formations known as maria that are present on the Moon. Its folds and scars indicate Mercury's contraction during a certain juncture in its history. The closeness of Mercury to the Sun has posed various observational challenges for terrestrial scientists, which are being tackled by spacecraft missions including Messenger, launched in 2004, that performed 2 flybys of the planet in 2008. And is scheduled for another in 2009 before entering orbit in 2011. Researchers have employed this property to corroborate the predictions of relativity theory concerning gravity's effect on space and time. Mercury is an intense planet in various dimensions. Owing to its proximity to the Sun, averaging 58 million kilometers, 36 million miles, in orbital distance, Mercury has the shortest orbital period, 88 days, and endures the highest intensity of solar radiation of all planets. Mercury, with a radius of roughly 2,440 kilometers, 1,516 miles, is the smallest notable planet, inferior in size to both Ganymede, the largest moon of Jupiter, and Titan, Saturn's largest moon. Furthermore, Mercury exhibits a very high density. Although Mercury has a mean density similar to Earth's, it has less mass and undergoes diminished gravitational compression. Its weight is the greatest among the planets when accounting for self-compression. About 2/3 of Mercury's mass consists of its mostly iron core, extending from the planet's center to a radius of roughly 1,800 kilometers, or 3/4 of the distance to its surface. The lithosphere of the planet, consisting of the surface crust and the underlying mantle, exceeds a thickness of 600 kilometers, 400 miles. At sunset and twilight, the Earth's surface conceals Mercury, which never attains an angular separation more than 28 degrees from the Sun. The synodic period of Mercury is the time taken for successive elongations, when Mercury re-emerges at the same location relative to the Sun in the morning or evening sky, is roughly 116 days. The Earth's turbulent atmosphere continually obstructs Mercury's visibility due to its proximity to the horizon. Even outside the atmosphere, orbiting observatories such as the Hubble Space Telescope are limited by the great sensitivity of their sensors, preventing them from orienting sufficiently towards the Sun to study Mercury. Due to Mercury's orbit being aligned with Earth's, it periodically transits directly between Earth and the Sun. A planet is observable through a telescope or spacecraft as a little black dot traversing the Sun's luminous disk. This phenomenon is referred to as a transit, occurring approximately 12 times each century. Mercury presents obstacles for exploration by a space probe. Owing to the planet's location within the Sun's gravitational influence, a considerable amount of energy is necessary to modify a spacecraft's trajectory from Earth's orbit to that of Mercury, facilitating either orbital insertion around the planet or surface landing. Mariner 10, the first spacecraft to investigate Mercury, executed 3 brief flybys in solar orbit between 1974 and 1975, contributing to planning subsequent missions to Mercury, including those by the US. The Messenger spacecraft, launched in 2004, employed complex paths designed by aerospace engineers, utilizing gravitational aids from several flybys of Venus and Mercury over several years. The Messenger mission plan indicates that the spacecraft will commence a prolonged orbit around Mercury in 2011 for comprehensive study. This will follow observations from modest distances during planetary flybys in 2008 and 2009. Furthermore, the extreme heat emanating from the Sun and then re-radiated by Mercury has presented considerable difficulties for spacecraft engineers in regulating the functioning temperature of sensors. Mercury's orbit has the largest inclination among the planets, deviating nearly 7 degrees off the ecliptic, the plane defined by Earth's orbit around the Sun. It is also distinguished by the highest eccentricity of any planetary orbit. The elongated orbit results in the Sun appearing more than twice as luminous in Mercury's sky at perihelion. When the planet is 46 million kilometers, 29 million miles, from the Sun, in contrast to aphelion, which is approximately 70 million kilometers, 43 million miles, distant. Mercury's sidereal day, lasting 58.6 Earth days, causes a slow westward motion of the Sun in its sky. Mercury's orbit around the Sun causes its rotation and revolution periods to align, leading to the Sun completing a full circuit in 3 Mercurian sidereal days, similar to 176 Earth days, defining the duration of its solar day. Per Kepler's rules of planetary motion, Mercury orbits the Sun with such velocity near perihelion that the Sun appears to switch direction in Mercury's sky, briefly going eastward before resuming its westward path. The hot poles are the 2 locations on Mercury's equator where this oscillation occurs midday. Due to the continuous overhead light, surface temperatures could exceed 700 Kelvin, 430 degrees Celsius, or 800 degrees Fahrenheit. The 2 equatorial regions located 90 degrees from the hot poles, known as warm poles, do not attain similar temperatures. From the perspective of the heated poles, the Sun appears low on the horizon and is about to set when it reaches its zenith and performs its brief course reversal. At Mercury's northern and southern rotational poles, surface temperatures may plummet to negative 100 degrees Fahrenheit under oblique sunlight conditions. During Mercury's prolonged dark phases preceding sunrise, surface temperatures fall to roughly negative 300 degrees Fahrenheit. Mercury displays the most significant temperature variation among the solar system's 4 inner terrestrial planets. Nonetheless, its night side would endure even lower temperatures if Mercury had synchronous rotation, with one hemisphere perpetually oriented towards the Sun and the other in constant darkness. Before Earth-based radar studies in the 1960s, astronomers had long believed that Mercury's rotation was synchronous with its 88-day orbital cycle. Telescopic viewers could only observe Mercury during particular periods of the year due to its angular separation from the Sun. The presumption that Mercury's surface's consistent, subtly perceptible characteristics signified a uniform rotational velocity deceived them. The radar studies revealed that the planet's rotation period of 58.6 days is distinct from its orbital period and is exactly 2/3 of that time. Mercury completes 3 rotations for every 2 orbits around the Sun. This is probably due to its orbital eccentricity and the significant solar tides, which alter the planet's structure induced by the Sun's gravitational influence. Tidal forces likely slowed Mercury's spin during its creation. Instead of slowing to a condition of synchronous rotation as seen in many planetary satellites, including Earth's moon, Mercury became trapped with a rotation period of 58.6 days. At this rate, the Sun exerts a continuous and notably strong gravitational force on the tidally generated bulges in Mercury's crust at the higher poles. The tidal friction between the young planet's solid mantle and molten core markedly enhanced the probability of recording the spin during daylight hours. The gravitational influences of the Sun and other planets on Mercury have significantly impacted its orbital motion, enhancing the formulation and validation of gravitational theories. The phenomenon appears as rotation or precession of Mercury's orbit around the Sun. For 2 centuries, it has been established that the Sun traverses around 9.5 arc minutes, 0.16 degrees of arc per century. Isaac Newton's gravitational theory accounts for almost 93% of this motion, or 43 arc seconds, 0.012 degrees of arc. Nonetheless, the disparity was too substantial to overlook, leading to reasons that often cited the possibility of undiscovered planets near Mercury's orbit. In 1915, Albert Einstein illustrated that incorporating gravity into his general theory of relativity could clarify the little disagreement. Thus, the precession of Mercury's orbit served as a crucial observational confirmation of Einstein's theory. Thereafter, Mercury was utilized to further test relativity. These were predicated on the notion that radar signals reflected from its surface during superior conjunction, when positioned on the other side of the Sun from Earth, necessitated traversal near the Sun. Suna's general theory of relativity posits that electromagnetic signals traversing space distorted by intense gravitational forces will follow a marginally altered trajectory and require longer to traverse that space than conditions devoid of the Sun's presence. Through the comparison of reflected radar signals with precise predictions derived from the general theory, we identified a second significant corroboration of relativity. The 3 flybys of Mariner 10 furnished scientists with the majority of their understanding of Mercury. The spacecraft established an orbit around the Sun. The spacecraft synchronized with one Mercurian solar day, ensuring that each of its 3 orbits corresponded with the illumination of the same hemisphere of the planet. The mission ultimately obtained photographs of roughly 45% of Mercury's surface, marginally less than the sunlit hemisphere. Mariner 10 collected data on particles and magnetic fields throughout its flybys, which included 2 close encounters on the night side and 1 far approach on the day side. Researchers discovered an unexpectedly Earth-like, but considerably weaker magnetic field on Mercury. Researchers could not anticipate a planetary magnetic field for an object of such diminutive size and sluggish rotation. This is due to the dynamo hypotheses, which required completely molten cores and rapid rotations for explanation. Celestial entities with much more rapid rotation, such as the Moon and Mars, lack magnetic fields. Moreover, Mariner 10's spectrum analyses revealed that Mercury has a very sparse atmosphere. The early significant telescopic studies of Mercury after the Mariner mission resulted in the discovery of sodium in its atmosphere in the mid-1980s. Subsequently, improved methodologies on Earth enabled the observation of temporal and spatial variations in Mercury's atmosphere. Furthermore, advancements in ground-based radar technology enhanced its capabilities and sensitivity, creating intriguing maps of the hemisphere that Mariner 10 had not previously observed. Condensed water ice was detected in persistently shaded craters near the poles. In 2008, the Messenger probe executed its first flyby of Mercury, obtaining photographs of more than one-third of the hemisphere that had not been previously viewed by Mariner 10. The probe came within 200 kilometers, 120 miles, of the planet's surface, and detected various previously unidentified geological characteristics. The goal is for Messenger to attain orbit around Mercury in 2011 and conduct a year-long research. Mercury is both small and hot, due to its incapacity to keep a significant atmosphere if it ever had one. The surface pressure on Mercury is under 1/1,000,000th of that on Earth. Nevertheless, the detected traces of atmospheric components have revealed intriguing planetary behaviors. Mariner 10 identified minuscule amounts of atomic helium and even smaller amounts of atomic hydrogen near Mercury's surface. Most of these atoms derive from the solar wind, a flow of charged particles released by the sun. Sunt spread around the solar system, briefly residing near Mercury's surface for hours before exiting the planet. The Mariner additionally verified the presence of atomic oxygen via subsequent telescopic observations. The oxygen likely derives from Mercury's surface soils or meteoroids that strike the planet, scattering particles into the atmosphere by collision or solar wind bombardment. The brilliant dawn sunlight disperses the atmospheric gases accumulating on Mercury's night side. The interaction of energetic particles from the solar wind with Mercury's magnetosphere ionizes many atoms in the planet's surface rocks and scant atmosphere. In contrast to Mariner 10, the Messenger spacecraft is equipped with equipment intended for ion measurement. In its first flyby of Mercury in 2008, Messenger identified several ions, including oxygen, sodium, magnesium, potassium, calcium, and sulfur. The measured amounts of sodium and potassium at the surface range from several hundred to tens of thousands of atoms per cubic centimeter. Telescopic spectral instruments exhibit high sensitivity to these two elements. This enables astronomers to observe thicker regions of these gases traversing Mercury's disk and its surrounding space, despite their minimal presence. The origin and destination of these gases held mostly theoretical significance rather than practical relevance until the early 1990s. Only persistently shaded regions of deep, near-polar craters appear to harbor them. Researchers propose that the reflective material could be water ice. The idea that the planet nearest to the Sun initially harbored significant water ice deposits seemed improbable. Nevertheless, Mercury must have accumulated water, maybe from crashing comets. Water ice on Mercury's extreme surface will immediately sublimate, resulting in the individual water molecules dispersing in random ballistic trajectories. The probability of a water molecule colliding with another atom in Mercury's atmosphere is extremely low. However, dissociation may occur owing to intense sunlight. Calculations suggest that after multiple hops, roughly 1 in 10 water molecules eventually reside in a deep polar depression. Mercury's rotational axis is almost orthogonal to its orbital plane, resulting in sunlight being practically horizontal at the poles. Under these conditions, the foundations of deep depressions would consistently remain obscured, forming cold traps capable of retaining water molecules for millions or billions of years. A polar ice deposit would accumulate gradually. The ice's vulnerability to progressive sublimation, such as from the gentle warmth of sunlight, may be reduced due to the negligible heat reflected from remote mountains or crater rims. The process could be halted if the ice gradually became enveloped in a layer of insulating material known as regolith. Regolith consists of dust and rock fragments ejected by distant collisions. The volatile substance near Mercury's poles cannot be unequivocally identified as water ice. Moreover, radar investigations identified minor regions exhibiting elevated reflectivity at latitudes as low as 71 degrees, an improbable location for the formation and retention of water ice. Moreover, we have applied the same reasoning concerning the possible existence of water ice near Mercury's poles to the Moon, where accumulation is anticipated to be more significant. We have found indications of, at most, little water ice near the lunar poles. Mercury may have cold-trapped, an additional volatile material with lower evaporation tendencies than water. Atomic sulfur is comparatively abundant in the cosmos and may be especially prevalent on and within Mercury for several reasons. Mariner 10's observations indicate that Mercury's magnetic field, albeit only 1% as strong as Earth's, displays a dipolar configuration aligned with the planet's rotating axis. Remnant magnetism is another possible explanation for the field's presence, denoting the remaining imprint of an old magnetic field incorporated into the rocks throughout the crust's cooling process. Currently, most scientists assert that it is generated by a magnetohydrodynamic dynamo process, the motion of an electrically conductive fluid, in the outer portions of the iron core, analogous to the generation of Earth's magnetic field. Data from Messenger's magnetometer, obtained during the spacecraft's inaugural flyby in January 2008, confirm that Mercury's magnetic field is primarily dipolar. The absence of crustal contributions from remnant magnetism suggests that Mercury's dynamo is operational. Mercury's magnetic field deflects the solar wind with a teardrop-shaped magnetosphere, whose rounded end reaches outward toward the Sun, roughly 1 planetary radius from the surface. This represents only 5% of the sunward extent of Earth's magnetosphere. Mercury's atmosphere is so insubstantial that it lacks an equivalent to Earth's ionosphere. Calculations demonstrate that the solar wind can, at times, exert enough force to propel the sunward border, magnetopores, of the magnetosphere beneath Mercury's surface. In these conditions, solar wind ions would impact the portions of Mercury's surface directly beneath the Sun. Such rare instances of an event could substantially alter the atomic structure of surface components. Preliminary data from Messenger suggests that Mercury's magnetosphere may exhibit a unique structure identified as a double magnetopores. A significant amount of heavy ions, primarily sodium, may result from the planet's surface and atmosphere. Geophysicists and space scientists are investigating Mercury's magnetospheric processes to validate their understanding of Earth's magnetosphere by examining a comparable system characterized by a distinct scale and solar wind environment. For example, Mariner 10 equipment identified rapidly varying energetic particles in the planet's magnetotail, the extended portion of the magnetosphere situated downstream from the planet's night side. This activity mimicked geomagnetic substorms on Earth associated with auroral occurrences. The genesis of such phenomena on Earth may be better understood by the comprehensive global data that Messenger will gather upon entering orbit around Mercury in 2011. The regions of Mercury designated as Mariner 10 and Messenger resemble the Moon. Mercury is significantly characterized by impact craters of diverse dimensions. The tiniest craters are observable in the highest resolution Mariner image. Mercury is substantially characterized by impact craters of varied sizes. More extensive craters are relatively level, less cratered regions known as intercrater plains. These are comparable to, but considerably more expansive than, the light-colored plains found in the intercrater areas of the highly cratered lunar highlands. Sparsely cratered regions, or calm plains, surround Mercury's most prominent impact feature, the expansive Caloris Impact Basin. The Mariner 10 missions lit barely half of this basin, whereas Messenger's initial flyby in January 2008 provided a comprehensive revelation. The primary topographic characteristics of Mercury are the craters that cover a substantial part of its surface. Although generally similar to lunar craters, Mercurian craters reveal intriguing differences upon closer inspection. The surface gravity of Mercury is more than double that of the Moon, mainly due to the planet's significant iron core. Material expelled from a crater can only go 65% of the distance achievable on the Moon because of the heightened gravitational force. This may elucidate why Mercury possesses more secondary craters than primary craters, which are formed when asteroids or comets directly impact the planet. Secondary craters are formed when debris is ejected into space, impacting the Earth. The augmented gravity facilitates bigger craters' complex shapes and formations, including center peaks and subsidence. The superior gravity of Mercury, relative to the Moon, leads to the formation of smaller craters. The tiniest craters on Mercury have a diameter of around 10 kilometers, 6 miles, while the greatest craters on the Moon are about 19 kilometers, 12 miles. The diminutive craters include central peaks, crumbled walls, and flat floors, features commonly linked to larger craters. Two planets exhibit comparable surface masses. Recently created craters on Mercury are often deeper than craters of comparable dimensions on Mars. This may be due to a reduced presence of volatile chemicals in Mercury's crust, or the increased velocity of solar orbiting particles as they approach the Sun. Sun craters on Mercury exceeding 100 kilometers, 60 miles in diameter, have characteristics indicative of evolving into the bullseye configuration, characteristic of the largest impact basins. The structures mentioned above, known as multi-ring basins and exceeding 300 kilometers, 200 miles in diameter, are the consequence of the most vigorous impacts. We tentatively discovered several multi-ring basins in the imaged area of Mercury. Recent messenger photos and laser altimetry will improve our understanding of the remnants from historical asteroid collisions on Mercury. The temporal study will greatly assist in clarifying these remnants from the planet's initial asteroidal bombardment. Directly opposite Caloris, exactly 180 degrees apart, is a region marked by exceptionally deformed topography. The Caloris impact focused seismic waves on Mercury's surface at the antipodes, suggesting it transpired concurrently. It ascends to roughly 1 mile, 1 kilometer, in elevation. The seismic activity that sculpted the terrain modified the existing crater rims, forming hills and cracks. Numerous craters display smooth surfaces. The seismic activity that sculpted the terrain modified existing crater rims, forming hills and cracks. The unblemished, even surfaces of specific craters indicate a later material deposition on Mercury. Plains, relatively flat or gently undulating landscapes, are common on Mercury and the other terrestrial planets. They constitute a basis upon which further landforms arise. Resurfacing is the procedure of covering or eliminating irregular terrain to establish a more uniform surface, and plains serve as proof of this occurrence. At least 3 mechanisms for planetary resurfacing may have contributed to the formation of Mercury's plains. One method: elevating the temperature reduces the... There are at least 3 methods for planetary resurfacing, all of which may have contributed to the formation of Mercury's plains. More than 200 fractures, analogous in magnitude to the ridges, radiate from the core of Caloris. Multiple defects define these depressions. More than 200 cracks, comparable in dimensions to the ridges, radiate from the center of Caloris, happening after the creation of the ridges. Caloris is encircled by 2 types of terrain: the basin rim and the basin ejecta. A notably steep escarpment defines the core of Caloris. A secondary, considerably smaller escarpment ring is located roughly 100 to 150 kilometers, 60 to 90 miles, beyond the original escarpment. Flat plains occupy the valleys between mountain ranges. Beyond the external escarpment exists a region defined by linear radial ridges and valleys, partially inhabited by plains, some of which contain numerous knobs and hills with diameters of only a few hundred meters. The origin of these plains, forming a broad ring around the basin, has been disputed. Specific lunar plains predominantly originated from the impact of basin ejecta on the pre-existing surface produced during basin creation. This may have also occurred on Mercury. Nevertheless, the messenger findings suggest a substantial role of volcanism in forming many plains. The annulus exhibits fewer craters than the interior plains of Caloris, indicating that its formation occurred over an extended duration. It possesses additional characteristics more explicitly associated with volcanism than those depicted in Mariner 10 pictures. Images from Messenger illustrating volcanic vents, primarily situated near the margins of Caloris, provided definitive evidence of volcanism. Caloris is one of the most recent, extensive, multi-ring basins identified on Mercury. It originated concurrently with the last significant basins on the Moon, some 3.9 billion years ago. Messenger photos revealed a diminutive basin, distinguished by a prominent inside ring, likely formed more recently and identified as Raditladi. A second approach involves the displacement of material to lower elevations due to gravitational pressures. This material eventually gathers in depressions, elevating as more volume is added. The comparatively young plains on Mercury, especially those illuminated by a low sun during Messenger's initial flyby, display notable volcanic features. The interior operates in this manner. A third process entails depositing material from above onto a surface, initially concealing the uneven topography and eliminating it entirely. Lava flows have inundated ancient craters like those filled with lava on the Moon and Mars. Nonetheless, the vast intercrater plains on Mercury provide significant problems for evaluation. Owing to their age, any significant volcanoes or volcanic features may have undergone erosion or destruction, complicating conclusive identification. Understanding these ancient plains is crucial, as they appear to be associated with the obliteration of more craters on Mercury, measuring 10 to 30 kilometers in diameter, in contrast to those on the Moon. The primary landforms on Mercury that elucidate the planet's mostly concealed interior processes are its many lobate scarps. The cliffs extend from a few tens to over 1,000 kilometers in length, and from around 100 meters to 3 kilometers in height. They display curved or scalloped edges when viewed from above, thereby earning the term lobate. An elevated surface segment above the adjacent terrain generates fractures called faulting. Local horizontal compressive pressures within the crust inhibit the advancement of thrust faults on Earth. The distribution of these characteristics throughout Mercury's entire imaged surface indicates that the planet's crust has experienced a worldwide contraction in the past. The dimensions and arrangements of the lobate scarps indicate that the planet's diameter has diminished by at least 3 kilometers, 2 miles. Mercury's geological history indicates that it has undergone contraction until very recently, particularly with the formation of Caloris. Lobate scarps demonstrate alterations in the morphology of comparatively recent impact craters. Tidal forces would have induced compression in Mercury's equatorial latitudes by slowing the planet's initial high rotation rate. The globally widespread lobate scarps indicate an alternate hypothesis: the gradual cooling of the planet's mantle, possibly resulting from solidifying a segment of its previously totally liquid core. This led to the contraction of the core and the distortion of the cold surface crust. Due to the cooling of Mercury's mantle, the planet is expected to exhibit more compressional structures on its surface than are presently observed. This indicates that the planet continues to diminish in size. Researchers have determined the composition of Mercury's surface by analyzing sunlight reflected from different regions. A significant difference between Mercury and the Moon is that Mercury exhibits a more restricted range of surface brightness and is predominantly darker. The Moon's Maria, visible as vast dark areas to the unaided eye, are much darker than its cratered highlands, whereas Mercury's plains are slightly darker than its cratered zones. The color differences on Mercury are less pronounced than those on the Moon. Still, photos obtained by MESSENGER via several color filters have revealed subtle regions, primarily associated with volcanic vents, that display significant colors. Mercury's characteristics and limited light reflection suggest that its surface lacks an abundance of iron and titanium-rich silicate minerals, resulting in its darker appearance than the lunar mare. Mercury's rocks may specifically possess low oxidized iron FeO quantities. This indicates that Mercury originated in far more reducing conditions, marked by a deficiency of oxygen, compared to other terrestrial planets. The analysis of remote sensing data, encompassing reflected sunlight and thermal radiation spectra, complicates the assessment of Mercury's surface composition. The intense radiation from the proximate Sun renders the optical characteristics of mineral grains on Mercury's surface discernible, complicating straightforward conclusions. MESSENGER is equipped with various instruments absent on Mariner 10, enabling direct evaluation of chemical and mineral compositions. The equipment must observe Mercury for prolonged periods when the spaceship is close. Consequently, MESSENGER's 3 preliminary and succinct flybys yield no definitive conclusions. Scientists previously hypothesized that Mercury's elevated iron content compared to other terrestrial planets could be attributed to its formation from elements in the extremely hot inner area of the solar nebula, where only substances with high melting temperatures could solidify. The more volatile elements and compounds would not have solidified near the Sun. Nonetheless, current ideas concerning the solar system's creation fail to consider the possible impact of accretion on the chemical composition of planets as their distance from the Sun rises. The entities amalgamated to become Mercury probably stemmed from an extensive area of the inner solar system. Mercury may have evolved from the asteroid belt or a region nearer to the Sun. Subsequent gravitational interactions among the various forming protoplanets may have moved Mercury. Certain planetary scientists propose that in Earth's formative history, following its chemical diversification into a less dense silicate crust and mantle, and a denser iron-rich core, a significant impact removed substantial portions of the planet's outer layers, leaving the core as the predominant component. This event resembles the effect of a Mars-sized object colliding with Earth, which is thought to have formed the Moon. However, these tumultuous and violent planetary origins would not necessarily place the densest planet closest to the Sun. Subterranean processes may have mostly led to Mercury's increased density. The aerodynamic drag of the gaseous solar nebula may have caused the materials that formed Mercury to segregate into denser metallic and lighter silicate particles. The planet's proximity to the primordial Sun has caused its silicates selective evaporation and depletion. Each scenario predicts unique bulk chemistry for Mercury. Moreover, the influence of infalling asteroids, meteoroids, and comets, in conjunction with the deposition of solar wind particles, has been modifying or augmenting Mercury's surface and subsurface minerals for billions of years. Examining old Mercury and its processes is difficult due to the advanced capabilities of telescopes and spacecraft in analyzing these materials. Planetary scientists are confounded by the timeline of major geological and geophysical occurrences on Mercury after its genesis. It is enticing to replicate the Earth's history based on that of the Moon, whose chronology has been accurately determined from the rocks collected by the United States, Apollo crewed landings and Soviet lunar robotic missions. Likewise, Mercury probably experienced a similar history. However, the planet cooled and became geologically dormant shortly after the Caloris impact, unlike the Moon, which saw extended volcanism for hundreds of years. If asteroids, comets, and planetary debris collide with Mercury as they do with the Moon, most of its craters would have formed before and during a significant bombardment in the inner solar system. The lunar bombardment period ended 3.8 billion years ago. In addition to intermittent cratering, Caloris probably originated during that era, indicating the final stage of Mercury's geological history. Conversely, multiple data suggest that Mercury is geologically active. The dipolar field requires a partially molten core to sustain the magnetohydrodynamic dynamo. Recent radar studies of Mercury's rotational condition suggest that at least the outer core remains in a molten state. Moreover, as previously noted, Mercury's scarps display evidence suggesting that the planet may not completely experience cooling and contraction. Various approaches exist to resolve the seeming conflict between a planet that ended geological activity before the Moon and one that continues to exhibit geological activity. One hypothesis posits that most of Mercury's craters are more recent than those on the Moon and resulted from volcanoid impacts. Volcanoids are a theoretical population of asteroid-sized remnants orbiting the Sun within Mercury's orbit, which may have contributed to the formation of craters on Mercury over time. In this context, Caloris, the lobate scarps, and other features would be far younger than 3.8 billion years, indicating that Mercury is a planet whose surface has only lately become inactive as its warm interior cools. Notwithstanding thorough investigations, we have not yet located any volcanoids. Additionally, objects that closely orbit the Sun and exhibit high relative velocities may have been shattered in catastrophic collisions with each other in the remote past. A potential explanation for Mercury's thermal issue is that the outer layer of its iron core remains liquid due to pollution. The temperature anomaly on Mercury is presumably attributable to the liquid state of its iron core within the outer shell. This may stem from sulfur contamination, which lowers the metal's melting point, and radioactive potassium, which increases heat generation. The crust, distinctly visible during the creation of Caloris, impeded the volcanic vents that had produced significant volcanism earlier in Mercury's history. In this setting, while modern Mercury possesses residual interior heat and activity, surface processes have mostly halted except for a few thrust faults as the planet slowly compresses. No celestial body approaches Earth more closely than Venus, the second planet from the Sun. At its closest approach, it is the nearest significant celestial body to Earth, excluding the Moon. Venus's orbit is closer to the Sun than Earth's, causing the planet to continually appear near the Sun in the sky, and to be visible only during the hours around sunrise or sunset. It is the brightest planet in the sky when visible. Venus is the sixth largest planet in the solar system, regarding dimensions and mass. Venus was one of the 5 planets, together with Mercury, Mars, Jupiter, and Saturn, acknowledged in antiquity, and its motions were seen and scrutinized for ages before the advent of advanced astronomy gear. The Babylonians recorded its emergence, linking it to the goddess Ishtar in 3000 BCE. It is prominently cited in the astronomical records of various ancient civilizations, including China, Central America, Egypt, and Greece. Like Mercury, Venus was known by 2 different names in ancient Greece: Phosphorus when it appeared as a morning star, and Hesperus when it appeared as an evening star. The modern name originates from the Roman goddess of love and beauty, with the Greek equivalent being Aphrodite, probably because of the planet's luminous gem-like look. Due to their comparable masses, sizes, densities, and relative positions within the solar system, Venus is frequently referred to as Earth's twin. Their chemical composition is likely analogous, as they are produced in the solar nebula from comparable rocky planetary building components. Preliminary telescopic studies of Venus indicated a thick cloud cover suggestive of a significant atmosphere. This led many to conclude that Venus was a warm, humid planet, potentially akin to Earth in its primordial period. marked by swampy carboniferous forests and prolific life. Scientists now recognize that Venus and Earth have evolved significantly different surface conditions. It's unlikely that Earth-like life has emerged on Venus due to its severe temperatures, aridity, and other challenges. Researchers investigating Venus primarily seek to understand the causes of its severe conditions, which may yield crucial insights into the forces influencing environmental change on Earth. When viewed through a telescope, Venus displays a radiant yellow-white, largely uniform surface to the observer. An uninterrupted blanket of clouds obscures the planet's surface, increasing its concealed aspect. Cloud characteristics are difficult to identify in visible light. When observed at ultraviolet wavelengths, the clouds exhibit distinctive black marks, characterized by complex swirling patterns around the equator, and large V-shaped brilliant and dark bands heading toward the west. Before the early 1960s, scant understanding of Venus's surface, atmosphere, and evolution prevailed due to the ubiquitous clouds, until initial radar observations and spacecraft flybys emerged. Venus orbits the Sun at an average distance of 108 million kilometers, 67 million miles, roughly 0.7 times the distance of Earth from the Sun. It has the most circular orbit of any planet, varying from a perfect circle of only around 1 part in 150. Consequently, its distances at perihelion and aphelion, i.e. when nearest and farthest from the Sun, respectively, vary insignificantly from the mean distance. The orbital period of Venus, or the duration of a Venusian year, is 224.7 Earth days. The distance between Venus and Earth varies from roughly 42 million kilometers, 26 million miles, to a maximum of 257 million kilometers, 160 million miles, during their orbits around the Sun. Due to the overlap of Venus's orbit with Earth's, it displays phases akin to those of the Moon, as observed from Earth. Galileo's identification of these phases in 1610 was a key advancement in astronomy. In Galileo's time, the prevailing cosmological paradigm was based on the declaration of the Greek astronomer Ptolemy, made roughly 15 centuries earlier, which claimed that all celestial bodies revolve around the Earth. The observation of Venus's phases refuted this viewpoint while corroborating the heliocentric theory posited by the Polish astronomer Nicolaus Copernicus. Galileo's observation of the phases of Venus provided the first direct observational evidence for the Copernican theory. Venus demonstrates an unusual axial rotation for both orientation and speed. The Sun and most planets in the solar system rotate counterclockwise when viewed from above their north poles. This orientation is termed direct or prograde. Venus, however, rotates in a retrograde manner. Absent the planet's clouds, an observer on Venus's surface would watch the Sun rising in the west and setting in the east. Venus rotates slowly, taking around 243 Earth days to complete one rotation relative to the stars, establishing its sidereal day. Venus's rotational and orbital periods are almost coordinated with Earth's orbit, consistently presenting a similar face toward Earth when the planets are close. The reasons are complex and relate to the gravitational interactions between Venus, Earth, and the Sun, and the impact of Venus's dense revolving atmosphere. Venus exhibits little seasonal fluctuations because of its spin axis's minor 3-degree inclination about its orbital plane. Astronomers presently do not possess an adequate elucidation for the peculiar spinning properties of Venus. The majority of scientists concur that during the formation of Venus from planetesimals, it likely experienced a collision with a substantial body that caused proto-Venus to tilt and decelerate its spin. The mean radius of Venus is almost 95% of Earth's equatorial radius, and its mass is 4.87 times 10 to the 24th kilograms, representing 81.5% of Earth's mass. Earth's size and mass are equivalent to Venus's, resulting in a similar density. They exhibit comparable surface gravity. Individuals on Venus would experience roughly 90% of their Earth weight. Venus demonstrates a higher level of sphericity compared to most planets. The rotation of a planet generally causes equatorial bulging and polar flattening. Nevertheless, Venus's fast rotation allows it to maintain a nearly spherical shape. Venus has the most significant atmosphere among the inner solar system's planets. The atmospheric composition comprises more than 96% carbon dioxide and 3.5% molecular nitrogen. Trace gases are present, including carbon monoxide, sulfur dioxide, water vapor, argon, and helium. The atmospheric pressure at the planet's surface varies with altitude. The average radius is roughly 95 bars, or 95 times the atmospheric pressure at Earth's surface. The pressure in Earth's oceans is consistent at a depth of around 1 kilometer, 0.6 miles. Venus's upper atmosphere extends from the boundaries of space to roughly 100 kilometers, 60 miles, above its surface. The temperature varies considerably, reaching a peak surpassing lead and zinc's melting temperatures. The clouds surrounding Venus are exceptionally thick. The principal cloud layer in altitude ranges from roughly 48 kilometers to 68 kilometers. Additionally, tenuous hazes exist above and below the major clouds, extending from 32 kilometers to 90 kilometers above the surface. The higher haze is comparatively heavier in polar regions than in other areas. The principal cloud formation has 3 strata. All of them are quite delicate. An observer in even the most impenetrable cloud areas could perceive objects at distances of several kilometers. The cloud's opacity rapidly varies throughout space and time, signifying considerable weather activity. We have identified radio signals that signify lightning in the clouds of Venus. The cumulus clouds. Viewed from above, they display a luminous, yellowish tint, reflecting roughly 85% of the incident sunlight. The chemical responsible for the yellowish tint has not been definitively identified. The minute particles that make up the clouds of Venus consist of liquid droplets and even solid crystals. The principal ingredient is concentrated sulfuric acid. Supplementary materials may include solid sulfur, nitrosiles, sulfuric acid, and phosphoric acid. Cloud particles range from less than 0.5 micrometers, 0.00002 inches, in hazes to several micrometers in the densest layers. Specific regions at the cloud summit display darkness under UV illumination. However, the fundamental reasons remain predominantly unknown. Certain chemicals, such as sulfur dioxide, solid sulfur, chlorine, and iron chloride, may exist in minimal concentrations above the cloud tops and can absorb UV light in specific locations. The circulation of Venus's atmosphere is remarkable and unique among the planets. Although the planet completes 3 spins in 2 Earth years, its atmospheric cloud forms fully encircle Venus in around 4 days. The wind at cloud levels moves from east to west at a velocity of around 100 meters per second, 360 kilometers per hour, 220 miles per hour. The considerable velocity decreases markedly with lower altitude, leading to lethargic surface breezes on the planet, typically not surpassing 1 meter per second, less than 4 kilometers per hour, 2.5 miles per hour. Solar heating induces tidal movements, delicately influencing the westward flow above the cloud canopy. Nevertheless, the principal source of Venus's dense atmospheric superrotation remains unknown, representing one of the most intriguing mysteries in planetary research. The observation of wind-transported materials yields the primary data concerning surface wind directions. Although the surface winds on Venus are not particularly swift, the atmosphere is exceedingly dense, enabling the movement of loose, fine-grained debris. This generates surface characteristics observable in radar imagery. Some landforms resemble sand dunes, while others are wind streaks, created by selective deposition or erosion happening downwind from topographical factors. The wind-related properties suggest that surface winds predominantly go toward the equator in both hemispheres. This pattern corresponds with the concept that fundamental hemispheric scale circulation systems, referred to as Hadley cells, exist in Venus's atmosphere. This model asserts that atmospheric gases rise when heated by solar energy at the equator, travel at high altitudes toward the poles, descend upon cooling at higher latitudes, and then flow toward the equator along the surface until they are reheated and rise again. Regional analyses indicate distinct divergences from the equatorward flow pattern. The influence of topography on wind circulation may lead to these variations. Venus's considerable atmosphere produces a pronounced greenhouse effect, significantly increasing the planet's surface temperature. Venus absorbs less solar radiation than Earth due to its radiant continuous cloud cover. Nonetheless, the lower atmosphere and the surface absorb the sunlight penetrating the clouds. The absorbed light increases the temperature of the surface and gases in the lower atmosphere, which then radiate this energy at infrared wavelengths on Earth. The Earth maintains a relatively low surface temperature by reflecting most of its energy into space. In contrast, Venus's thick carbon dioxide atmosphere and extensive cloud layers trap a considerable amount of infrared energy. The restricted radiation raises the temperature of the lower atmosphere, resulting in a surface temperature increase of several hundred degrees. Investigating the greenhouse effect on Venus has clarified greenhouse gases' intricate yet essential role in Earth's atmosphere. It has also enhanced our understanding of how individuals' energy usage and other behaviors affect Earth's energy balance. The basic layer of the Venusian atmosphere is situated above the ionosphere. The terminology signifies that it comprises charged entities referred to as ions. The solar wind, a stream of charged particles emitted by the sun, influences the upper atmosphere, forming these ions. The primary ions in Venus's ionosphere are oxygen ions, O+ and O+, and carbon dioxide ions, which produce infrared radiation. Venus does not possess an intrinsic magnetic field unlike most planets, including Earth. Measurements from orbital spacecraft suggest that Venus's dipole field is roughly 1/80,000th the strength of Earth's. The planet's sluggish rotation may contribute to the absence of a magnetic field, as the dynamo theory posits that rotation facilitates the movement of fluids within the planet, thereby generating the magnetic field. Venus may lack a magnetic field because a non-circulating fluid or solid core fails to maintain a dynamo effect. The solar wind, striking a planet at supersonic speeds, usually creates a bow shock on the planet's sun-facing side, a stationary plasma wave that slows, warms, and redirects the flow around the globe. The planet's magnetic field sustains the bow shock at a considerable distance from the surface for specific planets. Jupiter's extensive magnetic field positions the bow shock approximately 3 million kilometers, 1.9 million miles, from the planet, in contrast to Earth's distance of about 65,000 kilometers, 40,000 miles. Without a detectable magnetic field, Venus's bow shock is only a few thousand kilometers above its surface, sustained exclusively by the planet's ionosphere. The proximity of the bow shock to the surface leads to extraordinarily powerful interactions between the solar wind and Venus's atmosphere. The ionopause, the top limit of the ionosphere, is located at a markedly lower altitude on Venus's day side than on its night side, attributable to solar wind pressure. The ionosphere demonstrates markedly greater density during the planet's daytime than nighttime. The interaction between Venus and the solar wind results in a steady and continual loss of hydrogen and oxygen from the planet's upper ionosphere into space, corresponding to a cumulative depletion of water from the planet. Throughout Venus's history, the cumulative volume of water lost via this mechanism may have amounted to several % of an ocean similar to Earth's. The high atmospheric pressure, low wind speeds, and especially harsh temperatures create a surface climate on Venus that is uniquely different from any other solar system. A series of landings by robotic Soviet spacecraft in the 1970s and early 1980s produced extensive surface chemistry and morphology data. Photographs of the Venusian landscape, illustrated by color images taken by the Soviet Union's Venera 13 lander in 1982, showcase rocky plains stretching toward the horizon. The yellow-orange light filtering through the clouds effectively brightens the surface despite the thick overcast. The rock's flat, slab-like, stratified composition is the most prominent characteristic of the surface of the Venera 13 site, as well as at most other Venera landing sites. Both volcanic and sedimentary rocks on Earth can display a similar appearance under appropriate conditions. Nevertheless, the explanation for the analogous appearance of Venusian rocks remains ambiguous. A darker, finely textured soil is also found among the rocks. Some soil particles were fine enough to be temporarily lifted into the atmosphere by the Venera lander, suggesting that certain grains have diameters of only a few tens of micrometers. Granule-sized particles that may comprise small stones or soil aggregates are scattered throughout the soil and on the rocks. The general surface aspect at the Venera landing sites is characteristic of Venus. However, it may not represent all areas accurately. The United States supplied the radar data. The Magellan probe, which orbited Venus in the early 1990s, provided extensive data on the roughness of the Venusian surface at scales ranging from meters to tens of meters. Vast lowland plains characterized by a smooth radar signature predominantly cover the planet. Nonetheless, some regions are significantly more mountainous. This includes areas impacted by ejecta, material blasted from impact craters and their vicinity, steep slopes associated with tectonic activity, and specific lava flows. From a lander's viewpoint, the characteristics of such terrains remain ambiguous. Still, it is anticipated that substantial boulders and other angular fragments would be more common than at the Venera locations. Several Soviet landers were outfitted with instruments to examine the chemical composition of Venus's surface components. We could not determine the types of rocks or minerals present by examining the relative quantities of merely a few components. We utilized two approaches to measure the abundance of various components. The Soviet Venera 8, 9, and 10 missions, together with the landers of the Vega 1 and 2 missions, employed gamma-ray spectrometers to assess the concentrations of naturally radioactive uranium, potassium, and thorium in the vicinity. X-ray fluorescence equipment on Veneras 13 and 14 and Vega 2 measured the amounts of several key elements. The Venera 8 location indicated that the rock composition may resemble granite or other igneous rocks on Earth's continents. Nevertheless, we derived this result exclusively from inaccurate measurements of the amounts of several radioactive elements. We measured radioactive materials at Venera 9 and 10 landing sites, as well as Vega 1 and 2. The mineral compositions of these rocks resemble basalt found on the marine floor and in volcanic areas like Hawaii and Iceland. The X-ray instruments of Venera 13, Venera 14, and Vega 2 measured the concentrations of silicon, aluminum, magnesium, iron, calcium, potassium, titanium, manganese, and sulfur. Despite the varying compositions of the three sites, the elements recorded by all three landers were analogous to those found in terrestrial basalts. An unforeseen result of Venus's orbital radar measurements is that the highest elevations exhibit abnormally high radar reflectivity. A thin layer of semiconducting material covers the highest heights, and the composition remains unidentified. However, an iron-bearing mineral such as pyrite or magnetite may have originated at cooler, elevated altitudes from low concentrations of iron, 2-chloride vapor in the atmosphere. Terrestrial observatories and Venus-orbiting spacecraft have provided extensive data on the planet's surface features. All have utilized radar equipment to navigate Venus's thick clouds. The planet's surface is completely desolate and uneven. In the lack of a definitive sea level, elevation is generally expressed as a planetary radius. indicating the distance from the planet's center to the surface at a particular location. We also utilize an alternative approach that measures elevation as the distance above or below the planet's mean radius. The majority of the Earth consists of gently undulating plains. In specific areas, the altitude fluctuates by only a few hundred meters over vast hundreds of kilometers. More than 80% of the Earth's surface deviates by less than 1 kilometer, 0.6 miles, from the average radius. Many locations on the plains exhibit vast, gently sloping topographic depressions, or lowlands, that can span several thousand kilometers in width. These include Atalanta Planitia, Guinevere Planitia, and Lavinia Planitia. Two notable features are the continent-sized highland areas or terrae, Ishtar Terra in the northern hemisphere, and Aphrodite Terra in the equator. In addition to the two primary landmasses, there are three minor raised areas: Alpha Regio, Beta Regio, and Phoebe Regio. Ishtar is the smaller of the two primary terraces, roughly equivalent in size to Australia. It extends roughly from latitude 45 degrees north to 75 degrees north, and from longitude 300 degrees east to 75 degrees east. Ishtar exhibits the most extraordinary topography on Venus, with several distinctive physiographic regions. The defining feature of western Ishtar is Lakshmi Planum, a raised, flat, lava-covered plateau. Mountain ranges surround Lakshmi on most of its boundaries, drawing comparisons to the plateau of Tibet. The eastern section of Ishtar displays geological intricacy, primarily consisting of tessera terrain. The initial examination of radar photos of Fortuna Tessera, the predominant feature of eastern Ishtar, reveals a highly rugged and deformed environment characterized by numerous parallel ridges and troughs intersecting at various angles. The geological processes that led to the development of Ishtar are not fully understood. Nonetheless, they presumably entailed the thickening of the Venusian crust, resulting from mantle motions. Aphrodite Terra is twice the size of Ishtar Terra and has an area similar to that of South America. It extends from around 60 degrees east to 150 degrees east longitude. Aphrodite's geography, more complex than Ishtar's, comprises several separate mountain ranges and deep, narrow basins. The western extremity consists of two large curving ridges, partially enclosing a broad circular region of irregular low-lying land. Two vast elevated sections comprise the majority of Aphrodite: Ovda Regio in the central region and Thetis Regio to the east. Ovda spans around 4,000 kilometers, 2,500 miles, from north to south, whilst Thetis stretches about 3,000 kilometers, 1,900 miles. The Tessera landscape is mostly composed of both elements. Aphrodite Terra intersects with a network of rift valleys and other tectonic formations near its eastern boundary. The geological processes that led to the development of Aphrodite remain undetermined, but most presumably involve the thickening of the Venusian crust due to mantle motions. Tectonic activity, or deformational movements inside the crust, explains several surface features of Venus. These include mountain ranges, plains deformation zones, rift systems, coronae, and tesserae. The mountain ranges on Venus's surface resemble those on Earth, such as the Himalayas in Asia and the Andes in South America. Prominent instances encompass those next to Lakshmi Planum, including Freya, Acna, and Danu Montes. Maxwell Montes is the most prominent mountain range on Venus. It is remarkably vast and comparable in magnitude to the Himalayas. It rises roughly 11 kilometers, 7 miles, above the planet's mean radius. The region was initially recognized as a significant characteristic in Earth-based radar scans of the globe in the 1960s, and was designated Maxwell in tribute to the British physicist James Clerk Maxwell, whose theories on electricity and magnetism form the foundation of radar technology. Subsequent radar scans from Earth and spacecraft revealed its mountainous features. A notable feature of Maxwell Montes is Cleopatra, a circular depression near its eastern boundary. Its diameter is just over 100 kilometers, 60 miles, and its depth is over 2.5 kilometers, 1.6 miles. Originally perceived as a volcanic caldera, Cleopatra attained significant attention as an impact crater. Maxwell Montes is one of the most prominent landforms on Venus in radar images. The increased radar reflectivity, which enabled early identification in the region, is partially due to its difficult terrain. An unknown material displaying significant radar reflectivity covers the high-altitude areas of Venus. This material could be an iron-containing mineral like pyrite or magnetite. The mountain ranges of Venus typically consist of parallel ridges and troughs separated by distances of 5 to 10 kilometers, 3 to 6 miles. They likely developed from the compression and thickening of the lithosphere, leading to the upward folding and thrusting of surface materials. In some respects, their creation resembles the formation of several mountain ranges on Earth. In contrast, their look differs from their terrestrial counterparts, since Venus lacks liquid water or ice. In the lack of rivers or glaciers for erosion, the mountain ranges of Venus have formed high inclines by folding and faulting. The slopes have gotten so steep in specific areas that they have collapsed under their weight. The erosional characteristics commonly found in terrestrial mountainous locations are lacking. Although plains deformation belts resemble mountain belts, they display less obvious relief and are primarily situated in low-lying areas of the planet, including Lavinia planitia and Atalanta planitia. They resemble mountain ranges and display significant evidence of parallel folding and faulting. The lithosphere can compress, deform, and elevate to produce them. In a particular lowland, deformation belts generally extend nearly parallel, usually distanced by several hundred kilometers. Rifts are some of the most extraordinary tectonic structures on Venus. The most advanced rifts are situated on vast elevated areas such as Beta Regio, sometimes radiating from their cores like the spokes of a giant wheel. Venus features extensive rift valleys, including Beta and other such regions. Significant portions of the lithosphere have been elevated from the Earth's surface. The rifts have several faults, with their floors typically located 1 to 2 kilometers below the surrounding terrain. The rifts on Venus resemble significant rifts observed in other regions, including the East African Rift on Earth and Valles Marineris on Mars. Volcanic activity appears to be associated with all these structures. The rifts on Venus are distinct from those on Earth and Mars because of the negligible erosion resulting from the lack of water. Coronae, derived from the Latin terms for garlands or crowns, are geological structures believed to result from hot, buoyant material known as diapirs, originating from the depths of Venus's surface. The formation of coronary arteries transpires in several phases. As diapirs rise through the Earth's interior and approach the surface, they can uplift the overlaying rocks, causing radial surface fracture. This generates a distinctive starburst pattern of faults and fractures, usually located on a broad, gently sloping topographic rise. These traits are sometimes termed novae, a label applied when their evolutionary relationship to coronae was less defined. As a diapir ascended towards the surface and underwent cooling, its buoyancy decreased. Consequently, the raised crust may descend under its weight, resulting in concentric faults. The result is a circular to oval arrangement of faults, fractures, and ridges. Volcanism may occur during all stages of corona development. In the later phases, it frequently obscures the radial faulting characteristic of the initial stages. Coronas typically spans several hundred kilometers in diameter. Despite having a noticeable outer rim, many coronae display considerable drooping in their interiors and beyond their rims. Venus displays many coronas at different stages of development. Radially cracked domes in their nascent stages are rare, whereas mature coronae, characterized by concentric scars, are some of Earth's most prevalent major tectonic features. Tesserae, Latin, mosaic tiles, denote the most geologically complex regions identified on Venus. Gravity readings reveal that the crust's thickness is largely uniform across the planet, with standard measurements between 20 and 50 kilometers, 12 to 30 miles. Possible anomalies encompass the Tessera highlands, where the crust may demonstrate significant thickness. The Tessera topography is prevalent in many vast high regions, including Alpha Regio. The topography appears highly rocky and markedly distorted in radar images, with many trends of parallel ridges and troughs that connect at various angles. Sometimes, Tessera terrain deformation is overly complex in determining the lithospheric stresses that induced it. No single mechanism can probably explain the complete development of tesserae. Tesserae typically appear luminous in radar imagery, indicating that the surface is irregular and fragmented at a meter-scale resolution. Tesserae may signify older terrain that has experienced greater mountain building and faulting relative to surrounding materials. Each occurrence influences the following one, resulting in the discerned complex pattern. Alongside substantial tectonic activity, Venus has seen extensive volcanism. The enormous lava fields that prevail across most rolling plains are the most significant volcanic eruptions. These exhibit substantial similarity to areas of overlapping lava flows found on other planets, including Earth, though they are markedly more extensive. The individual flows are primarily elongated and narrow, indicating that the erupting lavas had exceptional fluidity, enabling them to cover significant distances over mild slopes. Lavas on Earth and the Moon that display significant fluidity primarily consist of basalts, indicating their probable abundance on the plains of Venus as well. The elongated winding canals are the most notable of the diverse lava flow characteristics discovered on the Venusian plains. These meandering channels generally exhibit exceptionally consistent widths, extending up to 3 kilometers, 2 miles. They generally extend up to 500 kilometers, 300 miles, in width. One stretches 6,800 kilometers, 4,200 miles, in length. Low viscosity lavas that erupted at persistently elevated discharge rates presumably created the canali. Certain sections of the canali are elevating, indicating that the crust has undergone deformation post-channel formation, transforming the surface's mild descending gradients into ascending gradients. Additional channel-like volcanic formations on Venus consist of sinuous rills, maybe from collapsed lava tubes, and expansive, intricate valleys resembling those created by significant lava eruptions. In several regions of Venus, volcanic eruptions have formed structures similar to the massive volcanoes of Hawaii on Earth, or those associated with the Tharsis region on Mars. Sif Mons serves as a prime example of such a volcano. Located at the western edge of the elevated region Isla Regio, south of Ishtar Terra, it ascends roughly 2 kilometers and possesses a base diameter of 300 kilometers. More than 100 supplementary entities are widely dispersed worldwide. Known as shield volcanoes, they rise several kilometers above the surrounding plains and can extend hundreds of kilometers at their base. Numerous distinct lava flows are organized in a radial configuration, when a subsurface lava source remains stationary and active for an extended period, facilitating the accumulation of substantial volcanic material above it. The lava flows that form shield volcanoes are often elongated and slender, primarily composed of basalt, similar to those seen on the undulating plains. When a subterranean lava reservoir is exhausted, the surrounding terrain may collapse, creating a caldera depression. Numerous volcanic calderas are observed on shield volcanoes and amid the lava plains of Venus. They generally display a roughly circular form, akin to calderas observed on Earth and Mars. The peak area of Sif Mons features a caldera-like formation with a diameter of 40 to 50 kilometers, 25 to 30 miles. Many smaller volcanic formations are present alongside the extensive lava plains and the immense shield volcanoes. The plains contain numerous small volcanic cones. Pancake domes, distinguished by their atypical morphology, generally span several tens of kilometers in circumference and reach a height of around 1 kilometer, 0.6 miles, displaying a distinctly circular shape. A substantial mass of lava erupted from a central vent and momentarily radiated outward in all directions before hardening. They possess flat summits and precipitous flanks. The lavas that formed these domes displayed markedly higher viscosity than most lavas observed on Venus. Their composition remains unidentified. However, given our understanding of terrestrial lava, it is probable that they contain far more silica than the basalts prevalent in other regions. The distribution of volcanic formations on Venus is irregular. Despite its extensive extent, the Beta Atla Themis region, located between 180 degrees and 300 degrees east, exhibits remarkably elevated volcanic formations. The Venusian mantle in this location may have been actively rising over a vast expanse, leading to heightened heat flux and the formation of magma reservoirs. External entities and internal forces have altered the surface of Venus. Impact craters are dispersed over the terrain, created by meteorites that penetrated the atmosphere and struck the surface. Nearly all solid substances in the solar system have evidence of meteoritic impacts, with smaller craters often being more numerous than bigger ones. This general trend is also evident on Venus. Large craters several hundred kilometers wide are rare, while depressions measuring tens of kilometers in diameter and less are common. However, Venus exhibits an intriguing limitation: the absence of craters with dimensions less than 1.5 to 2 kilometers, 1 to 1.2 miles. The planet's dense atmosphere, which produces substantial frictional heating and intense aerodynamic forces upon the high-velocity entry of meteorites, explains their disappearance. The atmosphere slows and disintegrates smaller meteorites, while larger ones reach the surface intact. Craters, several kilometers in diameter, particularly those nearing the minimum observed size, generally do not have a circular form. Rather, they possess intricate forms, frequently characterized by several irregular indentations rather than a singular core depression. This indicates that the object that impacted the surface fragmented into multiple fragments, with each component striking it independently. Radar imagery also displays diffuse dark and bright smudges that may have resulted from the detonation of tiny meteorites above the surface. The significant craters observed on Venus display unique properties compared to those on other planets. Most impact craters on Venus and other celestial bodies display ejecta encircling them. Venusian ejecta is characterized by its edge, which often displays a flower petal or lobed morphology. This signifies that a considerable quantity is distributed horizontally across the ground, instead of rising vertically and falling back to the surface. This behavior was presumably induced by thick atmospheric gases infiltrating the flow, resulting in a turbulent cloud of gas and ejecta. A notable characteristic of extensive Venusian craters is the sinuous flows that originate from the ejecta, extending outward like lava flows. The intense pressures and temperatures during the impact liquefy the rock that constitutes these flows. The frequency of these flow patterns on Venus is mainly due to the planet's high surface temperature, bringing rocks closer to their melting point during crater formation, enabling more melt production compared to other planets. As a result, the molten rock will maintain its liquidity for a lengthy period, allowing it to cover significant distances. The most distinctive feature of Venusian craters relates to certain younger instances. In addition to the usual ejecta, Broad, parabola-shaped zones of black material partially surround these craters, a feature not found in other solar system locations. The parabola uniformly opens towards the west, with the crater at its eastern extremity. In radar images, black materials typically display smoothness at minute scales. The impact event likely launched fine-grained ejecta deposits upward, forming these parabolas. The swift westward winds around the planet appear to have gathered the debris after it rose above the Venusian atmosphere and fell back down. The material significantly dispersed downwind from the impact site, accumulating on the surface to form a parabolic pattern. Crater populations on planets and moons with impact craters provide essential data about the ages of their surfaces. The premise is clear. Older surfaces display more craters on any celestial body than younger surfaces. Establishing an accurate age in years is challenging, necessitating an indirect estimation of the crater production rate. The exact ages of materials on Venus's surface are unknown, yet the overall density of craters on Venus is lower than that observed on many other celestial worlds in the solar system. Estimates vary, but the average age of materials on Venus is below 1 billion years and may be considerably less. The distribution of craters on Venus is arbitrary. If craters were concentrated in particular regions, scientists could deduce that the planet displayed varied surface ages. The apparently arbitrary distribution of global craters indicates that the Earth's surface has seen multiple geological transitions over the past billion years, many of which transpired swiftly. Substantially less information exists concerning the interior of Venus in comparison to its surface and atmosphere. Nevertheless, scientists believe the planet has established a rudimentary parallel internal state because of its comparable size and density to Earth and its presumed formation from similar components. Thus, it contains a metallic core, a thick rocky mantle, and a less dense rocky crust. Venus's core, akin to Earth's, is probably primarily made of iron and nickel, but its comparatively lower density may indicate the existence of supplementary, less dense substances, such as sulfur. Unlike Earth, Venus lacks direct evidence of a metallic core due to the absence of an intrinsic magnetic field. Investigations of Venus's interior structure reveal that the outer edge of the core is around 3,000 kilometers, 1,860 miles, from the planet's center. The mantle of Venus, comprising most of the planet's volume, is situated above the core and the crust. Despite the high surface temperatures, the temperatures within the mantle are similar to those in Earth's mantle. Although made of solid rock, a planetary mantle can slowly deform or flow, similar to glacial ice, enabling significant convective movements. Convection significantly regulates the heating conditions of planetary interiors. Researchers contend that the decay of natural radioactive materials generates heat on Venus, similar to its impact on Earth. Convection transmits this heat to the surface. If temperatures within Venus were far higher than those on Earth, the viscosity of the mantle rocks would greatly drop, hence speeding convection and promoting more rapid heat dissipation. Therefore, we do not expect a substantial temperature difference between the deep innards of Venus and Earth. Convective currents in a planet's mantle can exert stress on surface materials. Activity within Venus's mantle may substantially influence the tectonic deformation evident in radar imaging. The gravitational field on Venus is more closely associated with the land's surface than on Earth, particularly in extensive regions with above-average altitudes. These regions also have elevated gravitational measurements. Elevated terrain lacks low-density roots to counterbalance its increased mass, unlike Earth. In contrast, several significant relief features on Venus may be directly linked to current convective activity in the mantle. Beta Regio exemplifies a high terrain potentially situated over regions of mantle upwelling. Lavinia planitia exemplifies a depressed topography potentially located over regions of mantle downwelling. Despite the numerous parallels between Venus and Earth, their geological evolution has significantly differed. Evidence suggests that plate tectonics is presently inactive on Venus. Mantle dynamics induce the deformation of lithospheric plates. Nevertheless, unlike Earth's plates, those within the lithosphere primarily do not exhibit horizontal movement relative to one another. Motions are primarily vertical since the lithosphere undergoes upward and downward deformation due to the underlying convective currents. Upwelling zones generally feature volcanism, coronae, and rifts, whereas downwelling regions primarily exhibit plains deformation belts. The formation of rugged uplands, such as Aphrodite and Ishtar, remains incompletely understood. Nonetheless, the process probably entails localized crust thickening due to mantle dynamics. Venus may lack plate tectonics if all other conditions remain constant, due to its higher surface temperature than Earth's. This causes Venus's lithosphere, its upper hard layer, to be more buoyant and less prone to subduction than Earth's lithosphere. Evidence indicates that Venus's lithosphere may be more substantial than Earth's and has developed throughout time. The gradual thickening of Venus's lithosphere over an extended period may be associated with the intriguing inference that most of the planet experienced a brief yet intensive phase of geological resurfacing less than 1 billion years ago, as indicated by its crater history. A plausible hypothesis is that Venus' mantle may intermittently experience global overturning. The lithosphere progressively thickens throughout these events until it experiences a near-global collapse, leading to a transient, widespread geological resurfacing event. The frequency and timing of this event over the planet's history are indeterminate. Following Galileo's discovery of the phases of Venus, terrestrial telescopes, radar, and an array of devices have performed extensive investigations of the planet. Over the years, telescopic astronomers, including Gian Domenico Cassini from France and William Herschel from England, have recorded various faint marks on its surface. Some markings may have aligned with current UV light cloud characteristics, while others may have been misleading. In the 1700s, scientists conducted notable early telescopic observations of Venus during its solar transits. During a solar transit, an object positions itself directly between the Sun and Earth, creating a temporary silhouette on the Sun's disk. Transits of Venus are rare events, occurring in pairs 8 years apart, with periods surpassing a century between each pair. These events were crucial to 18th century astronomy, as they provided the most accurate method for determining the distance from Earth to the Sun. The astronomical unit, or fundamental unit of astronomy, denotes this distance. The observations of the 1761 transit were only partially successful, although they prompted the original proposition by Russian scientist Mikhail Lomonosov that Venus has an atmosphere. In 1769, scientists correctly saw the second transit of the duo. Transits necessitate observation from several points on Earth to ascertain accurate distances, and the transits of 1761, particularly that of 1769, prompted numerous scientific missions to remote areas of the globe. The inaugural exploratory journey was undertaken by British Naval Commander James Cook, who, accompanied by scientists from the Royal Society, watched the transit of Venus from Tahiti in 1876, 1769. The transit observations of the 1700s not only provided a more accurate value for the astronomical unit, but also prompted some unrelated yet important discoveries about Earth's topography. By the time of the subsequent 2 transits in 1874 and 1882, the emerging discipline of celestial photography had advanced sufficiently for scientists to document their observations via telescopes on glass plates. In the 20th century, transits were absent. Nevertheless, in 2004, scientists meticulously recorded and documented the inaugural occurrence of the ensuing pair. In recent times, we have detected Venus at wavelengths outside the visible spectrum. Ultraviolet images definitively revealed the cloud formations in 1927 to 1928. In 1932, preliminary studies of Venus's infrared spectrum revealed that its atmosphere primarily comprises carbon dioxide. Subsequent infrared measurements clarified further aspects of the atmospheric composition and cloud development. Microwave observations conducted in the late 1950s and early 1960s indicated an increased temperature on Earth's surface. These observations necessitated the examination of the greenhouse effect to clarify these temperatures. Acknowledging that clouds completely conceal Venus, astronomers utilized alternative techniques to investigate its surface. Radar has been essential among these. When equipped with an appropriate transmitter, a big radio telescope can operate as a radar system to emit a radio signal toward a planet and capture its reflection. The technology efficiently investigates the planet's surface owing to the capacity of radio wavelengths to permeate the dense Venusian atmosphere. Radar observations of Earth have primarily been conducted from the Arecibo Observatory in the highlands of Puerto Rico, the Goldstone Tracking Station complex in the desert of Southern California, and the Haystack Observatory in Massachusetts. The first successful radar studies of Venus occurred at Goldstone and Haystack in 1961, revealing the planet's slow rotation, revolution. Later observations determined the rotation parameters with increased accuracy and began to unveil notable features on the planet's surface. We identified the initial features as Alpha Regio, Beta Regio, and Maxwell-Montes. By the mid-1980s, terrestrial radar technology had advanced, enabling Arecibo photos to see surface features as small as several kilometers. As a result, because Venus continuously presents virtually the same hemisphere to Earth during their closest approach, a substantial chunk of its surface has gone unseen from our planet. Robotic spacecraft have achieved notable advancements in the exploration of Venus. The first spacecraft to reach another planet and relay data was the United States Mariner 2, which performed a flyby of Venus in 1962. Since that time, Venus has been the subject of more than 20 satellite missions. The United States effectively executed initial Venus missions with Mariner 2, Mariner 5, 1967, and Mariner 10, 1974. As advancements in spacecraft and instrumentation, technology progressed concurrently. Each spacecraft conducted a singular near flyby, acquiring superior scientific data. After its mission to Venus, Mariner 10 executed a series of successful flybys of Mercury. In 1978, the United States launched the Pioneer Venus mission, comprising 2 complementary spacecraft. The orbiter achieved orbit around the planet, while the multi-probe launched 4 entry probes, 1 large and 3 smaller, targeting specific places within the Venusian atmosphere to collect data on atmospheric structure and composition. 17 scientific equipment equipped the orbiter to investigate the planet's atmosphere, ionosphere, and its interaction with solar wind. The radar altimeter produced the first high-resolution map of Venus's surface, Topography. The Pioneer Venus orbiter was one of the most long-lasting planetary spacecraft, relaying data for over 14 years. The Soviet Union's planetary exploration project concentrated on Venus during the 1960s, 1970s, and 1980s, yielding numerous significant accomplishments. After a preliminary series of failed missions, Soviet scientists deployed Venera 4 in 1967, comprising a flyby spacecraft and a probe that entered the planet's atmosphere. Equipped with a parachute and equipment for measuring atmospheric temperature, pressure, and density. It reached its goal on October 18th, signifying the first occasion of a human-made object navigating another planet's atmosphere and relaying data to Earth. Subsequent missions included the first successful soft landing on another planet, Venera 7 in 1970. The initial photographs relayed from the surface of another planet, Venera 9 and 10 landers in 1975. And the first spacecraft to enter orbit around Venus, Venera 9 and 10 orbiters. The paramount Soviet missions enhancing global comprehension of Venus were Veneras 15 and 16 in 1983. The twin orbiters delivered the first radar systems utilized on another planet, capable of producing high-resolution surface photos. We developed a map of Venus's northern hemisphere with a resolution between 0.6 and 1.2 miles. Venera 15 and 16 data identified or depicted in detail many geological characteristics currently acknowledged as present on the planet. The same year, the Soviet Union launched 2 more spacecraft to Venus, Venera 1 and Venera 2. The Venera-style landers released 2 balloons into the Venusian atmosphere, each lasting about 2 days while relaying data from their positions in the intermediate cloud layer. The Vega spacecraft advanced past Venus to conduct successful flybys of Halley's Comet in 1986. The United States initiated its most ambitious trip to Venus thus far. Initiated in 1989, the Magellan spacecraft achieved orbital insertion around the planet the same year, and performed studies until late 1994. A radar system integrated with Magellan generates images with a resolution above 100 meters, 330 feet. The spacecraft's almost polar orbit allowed it to monitor almost all latitudes on the Earth. Throughout each orbit, the radar system acquired an image strip around 20 kilometers wide, and typically surpassing 16,000 kilometers in length, extending nearly from pole to pole. We assembled the image strips into mosaics, producing high-resolution radar images of nearly 98% of the Earth. The radar altimeter system on Magellan assessed the planet's surface topography and particular material properties. Upon the completion of the principal radar goals of the mission, the spacecraft's orbit was slightly modified to enable multiple traversals of the upper limits of the Venusian atmosphere. The spacecraft's drag diminished its orbital energy over time, transforming its initially elliptical orbit into a low, circular trajectory. Subsequent planetary missions have utilized aerobraking to preserve substantial fuel by reducing thruster utilization for orbital modifications. From its new circular orbit, the Magellan probe successfully produced the first detailed map of Venus's gravitational field. In 1990, while traveling to Jupiter, the US Galileo spacecraft conducted a flyby of Venus. Notable findings included near-infrared photographs that traversed the atmosphere, disclosing the markedly varying opacity of the primary cloud layer. The US Cassini-Huygens spacecraft performed 2 flybys of Venus in 1998 and 1999 en route to its primary destination, Saturn. Contrary to previous spacecraft findings, the Cassini mission did not verify the existence of lightning in Venus's atmosphere. This suggested to some scientists that lightning on Venus is rare or different from Earth's. Initiated in 2005, the European Space Agency's Venus Express achieved orbit around Venus the subsequent year, marking it the inaugural European spacecraft to investigate the planet. Venus Express was outfitted with a camera, a visible light and infrared imaging spectrometer, and supplementary sensors to examine Venus's magnetic field, plasma environment, atmosphere, and surface, during a mission designed to last beyond 2 Venusian years. One of its primary accomplishments was obtaining the inaugural photographs of cloud formations above the planet's southern pole. Mars, the 4th planet in the solar system, is a conspicuous red entity in the nocturnal sky. It is denoted by the sign masculine and is the 7th largest planet in size and mass in the solar system. Historically, Mars, commonly called the Red Planet, has been linked to conflict and destruction. It is called for the Roman god of war. Approximately 3,000 years ago, Babylonian astronomer-astrologers named the planet Nergal, in reverence to their deity linked to death and pestilence. The planet has two moons, Phobos, fear, and Deimos, terror, named after the offspring of Ares and Aphrodite, representing Mars and Venus in Greek mythology. Recently, Mars has intrigued folks for more substantial reasons beyond its foreboding look. The planet is the second closest to Earth, after Venus, and is often easy to spot in the night sky because its orbit is external to Earth's. Telescopes on Earth can examine its solid surface and atmospheric processes, making it unique among planets. Centuries of meticulous research by terrestrial observers, augmented by satellite observations since the 1960s, have revealed that Mars possesses significant parallels to Earth. Like Earth, Mars features clouds, winds, a day length of around 24 hours, seasonal weather patterns, polar ice caps, volcanoes, canyons, and other discernible attributes. Evidence indicates that Mars bore a closer resemblance to Earth billions of years ago, including a denser, warmer atmosphere and abundant water, including rivers, lakes, flood channels, and potentially oceans. Mars presently resembles a desolate, icy desert. Yet intricate photos of water-eroded gullies suggest that small amounts of water may have flowed across the planet's surface in relatively recent geological periods, and might still exist as a liquid in protected underground areas. The lack of life, as we currently understand it on Mars, makes the existence of water a crucial issue. If microscopic life forms developed on Mars, they may endure in these hidden watery settings. In 1996, a group of scientists claimed to have discovered signs of ancient microbial life in a Martian meteorite. However, most scientists have disputed their interpretation. Since the late 19th century, Mars has been considered the most conducive environment in the solar system, following Earth, for indigenous life, human exploration, and colonization. During that period, many believed that the purported canals on Mars, intricate networks of elongated linear surface formations, observed by only a few scientists through telescopes, were constructed by sentient entities. Seasonal fluctuations in the planet's appearance, along with the growth and decline of vegetation, provided further proof of biological activity. Despite the canals being proven fictitious and seasonal variations attributed to geological rather than biological factors, scientists and the public remain interested in the prospect of extraterrestrial life on Mars and the exploration of other worlds. Mars has held a prominent role in popular culture throughout the past century. It has inspired multiple generations of fiction writers, including H.G. Wells and Edgar Rice Burroughs, at the height of the Martian canals, succeeded by Ray Bradbury in the 1950s and Kim Stanley Robinson in the 1990s. Mars has been a significant topic in radio, television, and film. Exemplified by Orson Welles' radio version of H.G. Wells is among the most notorious examples. Welles's novel War of the Worlds deceived numerous unwary listeners on the evening of October 30th, 1938, into believing that Martians were conquering Earth. The planet's fascination and myriad of authentic mysteries stimulate scientific inquiry and human ingenuity. Mars revolves around the Sun at an average distance of 228 million kilometers, 140 million miles, almost 1.5 times the distance from Earth to the Sun. Owing to Mars's elliptical orbit, the distance from Mars to the Sun varies between 206.6 million and 249.2 million kilometers, 128.4 million to 154.8 million miles. Mars orbits the Sun in 687 Earth days, signifying that its year is roughly double that of Earth's. Mars is located less than 56 million kilometers, 35 million miles, from Earth at its closest approach, while at its farthest, the distance can extend to about 400 million kilometers, 250 million miles, when the planets are on opposite parts of the solar system. Mars is most readily observable during its opposition to the Sun, when it is elevated in the sky and has a completely lighted surface. Successive oppositions transpire roughly every 26 months and may manifest at different locations inside the Martian orbit. Mars reaches its peak, brightness and size near the Sun and Earth, making it ideal for observation. Close oppositions transpire roughly every 15 years. Mars rotates on its axis every 24 hours and 37 minutes, resulting in a Martian day that is longer than an Earth day. The axis of rotation is about 25 degrees about its orbital plane, causing seasonal fluctuations on Mars akin to those on Earth. A Martian year consists of 668.6 Martian solar days, known as sols. Owing to the eccentric orbit, southern summers are more moderate and truncated, 154 Martian days. Unlike the northern areas, summers in the north are shorter and warmer, spanning 178 Martian days. Nonetheless, the conditions progressively change, resulting in shorter, warmer northern summers over 25,000 years. Furthermore, the axial obliquity, or tilt, progressively changes over an estimated 1 million year interval. The obliquity of Mars currently fluctuates between approximately 0 degrees, which results in no seasons, to as much as 45 degrees, causing significant seasonal fluctuations. Over a time scale of 100 million years, the obliquity may reach values as high as 80 degrees. Mars is a small planet, exceeding only Mercury and measuring just over 50% of Earth's size. The equatorial radius is 3,396 kilometers, 2,110 miles. But the mean polar radius is 3,379 kilometers, 2,100 miles. The mass of Mars is only 1/10 that of Earth, and its gravitational acceleration of 3.72 meters per second squared, 12.2 feet per second squared, near the surface suggests that items on Mars weigh little over 1/3 of their weight on Earth. Mars has only 28% of Earth's surface area, yet the land masses of both worlds are comparable, because more than 2/3 of Earth is covered by water. Ancient astronomers were confounded by Mars's seemingly irregular trajectory in the sky, alternating between direct or prograde motion, where it moved in the same direction as the Sun and other celestial bodies, and retrograde motion, which proceeded in the opposite direction. In 1609, German astronomer Johannes Kepler employed the remarkable naked-eye views of the planet made by his Danish colleague Tycho Brahe to empirically formulate its laws of motion, establishing the foundation for modern gravitational theory of the solar system. Kepler determined that Mars's orbit is elliptical, characterized by non-uniform yet predictable motion. Astronomers once developed their theories based on the outdated Ptolemaic model of hierarchical circular orbits and uniform speed. In 1610, the Italian astronomer Galileo performed the first telescopic observations of Mars, during which he identified the planet's disk. The original accurate surface marking representations are credited to the Dutch scientist and mathematician Christian Huygens. 1659 Huygens illustrated Mars, highlighting a significant dark region known as Syrtis Major. The Italian-born French astronomer Gian Domenico Cassini originally documented the Martian polar caps around 1666. Visual observers subsequently produced several notable findings. In 1669, Huygens ascertained the planet's rotation period, which Cassini later quantified in 1666 at 24 hours and 40 minutes, reflecting an error of only 3 minutes. The delicate Martian atmosphere was originally noted in the 1780s by German-born British astronomer William Herschel, who measured the tilt of the planet's rotating axis and conducted the inaugural analysis of Mars's seasons. In 1877, Asaph Hall from the United States. The Naval Observatory identified that Mars has 2 natural satellites. Telescopes have observed several meteorological and seasonal phenomena on Mars, including diverse cloud formations, the expansion and contraction of polar caps, and alterations in the hue and dimensions of dark regions according to seasonal changes. Many astronomers observed the presence of apparently linear patterns on the surface of Mars in the late 19th and early 20th centuries. These subjects incited significant discussion and influenced popular views concerning the possibility of extraterrestrial life. The Italian astronomer and statesman Giovanni Virginio Schiaparelli discovered around 100 of these patterns beginning in 1877 and described them as canali. Italian channels, a neutral term that implied no assumptions about their origin. Prior observers, like Pietro Angelo Secchi in 1858, had observed such patterns. Nonetheless, Schiaparelli's articles initially attracted much attention. At the onset of the 20th century, American astronomer Percival Lowell, who established an observatory in Flagstaff, Arizona, to examine Mars, advocated the theory that the planet's markings were extensive bands of vegetation alongside irrigation ditches or canals built by intelligent beings to convey water from the polar caps. Lowell and others illustrated canal networks intermingled with dark junctions called oases, covering a substantial amount of the planet's surface. At times, two parallel lines appeared where a solitary waterway had once been observable. Lowell produced progressively elaborate maps of the Martian canals until he died in 1916. The majority of astronomers found no canals and maintained suspicion about their existence. Experiments with untrained individuals showed that disjointed segments of diagrams or images could manifest as linear networks at appropriate distances. Telescopic photography through Earth's atmosphere yielded little resolution, as the lines were barely discernible to the human eye and surpassed the camera's recording capability. The dispute was resolved when detailed photos of the Martian surface were obtained by spacecraft, beginning with Mariner 4, 1965, and succeeded by Mariners 6 and 7, 1969. The surface displayed numerous craters and features but did not possess vast linear pathways, either natural or artificial. Beyond the polar caps, the Martian surface is characterized by bright red ochre areas marked with overlaid dark patterns, as observed from Earth-based telescopes. Historically, the illuminated areas were classified as deserts, while the broad, dark sections were formerly referred to as maria, Latin oceans or seas, singular mare, based on the presumption that they were submerged under large volumes of water. Telescopes located on Earth are unable to detect any topographical characteristics. We see variations in surface luminosity or changes in air opacity. The black markings cover almost 1/3 of the Martian surface, creating a band around the planet between 10 degrees and 40 degrees south latitude. We have seen their irregular distribution and variable growth patterns over decades to millennia. The northern hemisphere comprises three principal features: Acidalia planitia, Syrtis Major, and a black ring encircling the pole. These features were formerly considered to represent shallow marine environments or vegetation regions. It is now recognized that various dark regions on Mars are created and modified when winds move dark sand over the surface or remove patches of light dust. A considerable portion of the illuminated regions consists of dust accumulation zones. The canals, extensively illustrated on maps based on telescopic observations from the early 20th century, are not visible in detailed satellite imagery. These were probably false traits, experienced by observers trying to identify objects approaching the limits of their telescope's resolution. Early telescope observers noted a wave of darkening and a blue haze. These phenomena are now understood to stem from changes in observational conditions and fluctuations in the surface's reflecting properties. Telescopic observations reveal that Mars's most significant seasonal changes occur at the poles. As fall commences in one hemisphere, clouds accumulate over the corresponding polar region, and the frozen carbon dioxide cap expands. The northern cap extends to 55 degrees latitude whilst the southern cap reaches 50 degrees latitude. In spring, the ice caps recede. The northern carbon dioxide cap completely disappears during summer, leading to a reduced ice cap. In the summer, a little carbon dioxide and water ice residue remains in the southern region. The composition of the seasonal polar caps has been a subject of debate for about 200 years. The earliest theory that the caps were formed of water ice stems from English scientist William Herschel, who perceived them as analogous to those on Earth. 1898 Irish scientist George J. Stoney contested this hypothesis and suggested that the caps could harbour frozen carbon dioxide. However, evidence to support the hypothesis was unavailable until Dutch-American astronomer Gerard Kuiper identified carbon dioxide in the atmosphere in 1947. 1966 American scientists Robert Layton and Bruce Murray released results from a numerical model of Mars' thermal climate, greatly contesting the water ice concept. Their simulations indicate carbon dioxide in Mars's atmosphere would freeze at the poles. The fluctuations in their model's carbon dioxide caps corresponded with the actual behavior of the real caps. The model predicted that the seasonal ice covers were very shallow, measuring only a few meters near the poles and decreasing toward the equator. Although their findings were derived from simplified models of Mars, they were subsequently validated by thermal and spectral data obtained from the Mariner 6 and 7 spacecraft during their 1969 flybys of the planet. Early telescopic observers documented instances in which Martian surface features were briefly obscured. They observed white and yellow obscurations precisely ascribed to condensed gas and dust. Telescopic observers have documented the cyclical vanishing of all black marks, usually occurring during the southern summer. We precisely recognize them as a result of worldwide dust storms. Spacecraft observations have confirmed that hazes, clouds, and fog often conceal the surface. In 1947, Dutch-American astronomer Gerard P. Kuiper's telescopic observations confirmed that carbon dioxide is the primary constituent of the Martian atmosphere. The atmosphere is extremely thin, exerting less than 1% of Earth's surface atmospheric pressure. Surface pressures vary by a factor of 15 due to the substantial height fluctuations in Mars's geography. Negligible amounts of water presently exist in the atmosphere. If fully formed, it would result in a layer of ice crystals merely 10 micrometers, 0.0004 inches, thick, which might coalesce to create a solid block of ice approximately the dimensions of a medium-sized iceberg on land. Despite the restricted water supply, the atmosphere nears saturation, and ice clouds are abundant. Topographic depressions like valleys and craters often exhibit low-lying clouds and fog. Thin clouds often manifest at the morning terminator, the demarcation separating the sunlit and darkened areas of the planet's disk. Orographic clouds form when moist air rises over elevated land, cools, and often develops around prominent geological features like volcanoes and craters. Mid-latitudes often encounter westward-moving, spiral-shaped storm systems, similar to those on Earth in winter. Water ice is the primary constituent of many clouds, especially the white ones noted by early astronomers. Dust storms regularly transpire on Mars. They can occur at any time, but are most common during the southern spring and summer when Mars is near the Sun, and surface temperatures reach their zenith. The bulk of storms are localized and endure for several weeks. Every 2 to 3 years, dust storms reach a worldwide magnitude. At their climax, dust rises to elevations in the sky, where only the summits of the tallest volcanoes, extending up to 21 kilometers, 13 miles, beyond the Earth's mean radius, are discernible. Dust devils, undetectable from Earth, can be observed from Martian orbit at several spacecraft landing sites. High-resolution orbital photos reveal narrow trails, likely produced by dust devils. Unlike Earth's atmosphere, Mars' atmosphere experiences considerable seasonal variations in pressure when carbon dioxide, its predominant component, condenses as snow at the winter pole and sublimates back into gas during spring. The southern winter cap is larger than the northern counterpart, leading to a minimum air pressure during the southern winter when it reaches its maximum extent. The pressure varies annually by 26%, due to roughly 7.9 trillion metric tons of carbon dioxide entering and departing the atmosphere seasonally. This is equivalent to possessing a minimum of 23 centimeters, 9 inches, of solid carbon dioxide, dry ice, or many meters of carbon dioxide snow, distributed across the extensive marine region where seasonal polar caps exist. Carbon dioxide constitutes 95.3% of the atmosphere by weight, ninefold the quantity in Earth's considerably more extensive atmosphere. A substantial amount of Earth's carbon dioxide is chemically trapped in sedimentary rocks. But the concentration in the Martian atmosphere is less than 1/1000th of the total on Earth. The Martian atmosphere comprises molecular nitrogen, water vapor, and noble gases, including argon, neon, krypton, and xenon. Photochemical processes have generated several gases from the main constituents, including molecular oxygen, carbon monoxide, nitric oxide, and ozone. These gases are generally found in the stratosphere. The lower atmosphere supplies gas to the planet's ionosphere, defined by low densities, elevated temperatures, and the segregation of components via diffusion according to their masses. Various elements in the upper atmosphere are ejected into space, affecting the isotopic composition of the remaining gases. The Martian atmosphere comprises 5 times more deuterium than Earth, due to the selective loss of hydrogen relative to its heavier isotope, deuterium. Although a minor constituent of the Martian atmosphere, a few molecules per 10,000 at most, water substantially impacts atmospheric chemistry and meteorology, especially due to low atmospheric and surface temperatures. Water vapor completely saturates the Martian atmosphere. Nonetheless, the surface lacks liquid water. The planet's temperature and pressure are sufficiently low for water molecules to exist exclusively as ice or vapor. Despite the cold nighttime temperatures, the planet exchanges little water with the surface daily. Water vapor is equally distributed up to the altitude of vapor. The range is between 10 and 15 kilometers, 6 to 9 miles, displaying significant latitudinal gradients that fluctuate with the season. The most substantial changes occur in the northern hemisphere. During the northern summer, the complete lack of a carbon dioxide cap creates a water ice cap. The sublimation of water from the remnant cap generates a significant north to south concentration gradient of water vapor in the atmosphere. In the southern region, where a slight carbon dioxide cap endures over the summer and limited water ice has been seen. A notable water vapor gradient often does not develop in the atmosphere. The Martian soil is thought to engage with a considerably greater supply of ambient water vapor. Subsurface ice layers are common on Mars at latitudes over 40 degrees. Exceedingly low subsurface temperatures prevent ice melting. The 2001 Mars Odyssey mission confirmed the existence of ice within 1 meter of the surface at latitudes above 60 degrees, while the Phoenix lander identified ice below the surface at 68 degrees north. Nevertheless, the ice sheet's thickness is yet unknown. Conversely, ice is fragile in low latitudes, and any subsurface ice is likely to sublimate into the atmosphere. Diverse isotopic varieties suggest that the atmosphere previously had elevated carbon dioxide, nitrogen, and argon concentrations. Mars may have expended many volatile chemicals early in its history, either into outer space or the lithosphere, where they got chemically sequestered in rocks. Mars may have once had a considerably denser atmosphere that was diminished by chemical processes producing carbonates and massive asteroid impacts that ejected atmospheric gases into space. The vertical structure of Mars's atmosphere, particularly the changes in temperature and pressure with altitude, is governed by a complex interaction of many energy transport systems. How solar energy traverses the atmosphere and radiates into space affects the phenomena. Two variables dictate the vertical structure of the lower atmosphere: its composition, mostly carbon dioxide, and its significant concentration of suspended particulate matter. Carbon dioxide facilitates rapid atmospheric responses to fluctuations in solar radiation levels due to its effective energy radiation at Martian temperatures. The suspended particulate matter absorbs substantial amounts of heat from sunlight and is a scattered energy source in the lower atmosphere. Surface temperatures depend on latitude and display considerable fluctuation between day and night. At the Viking 1 and Pathfinder landing sites, situated at roughly 20 degrees north latitude, temperatures at a height analogous to human stature varied from a minimum of approximately 189 Kelvin, negative 84 degrees Celsius, or negative 119 degrees Fahrenheit, just before sunrise to a maximum of 240 K, negative 33 degrees Celsius, or negative 28 degrees Fahrenheit, in the early afternoon. The temperature variance is considerably more pronounced than in Earth's arid regions. The most significant change transpires close to the ground because of the sparse, arid atmosphere, which allows the surface to swiftly emit heat at night. This capability is reduced during dust storms, and the temperature fluctuation is lowered. The daily fluctuation is less perceptible at altitudes beyond several kilometers. However, other oscillations manifest in the atmosphere due to direct solar energy influx. The variations in temperature and pressure, referred to as tides due to their frequent occurrence in alignment with the Sun's position, provide a very intricate vertical structure to Mars's atmosphere. Atmospheric cooling with altitude happens at a rate of 1.5 Kelvin per kilometer, extending to around 40 kilometers, 25 miles, when the temperature stabilizes at around 140 Kelvin, negative 130 degrees Celsius, or negative 130 degrees Fahrenheit, minus 210 degrees Fahrenheit, a region referred to as the tropopause. The rate observed by the Viking and later Pathfinder spacecraft during atmospheric descent was unexpectedly low. Scientists had anticipated it to be over 5 Kelvin per kilometer. This rate is significantly lower than expected for clean air because of the considerable amount of suspended dust. The tendency of denser molecules to cluster below lighter ones determines the atmospheric composition beyond 100 kilometers, 60 miles. This diffusive separation mechanism reduces the tendency of turbulence to combine all components. At high altitudes, the absorption of UV energy from the sun dissociates and ionizes gases, leading to complex chemical processes. The high atmosphere has an average temperature of roughly 300 Kelvin, 27 degrees Celsius, or 80 degrees Fahrenheit. The atmospheric circulation patterns on Mars display certain superficial similarities to those on Earth, yet their fundamental reasons are significantly different. A notable feature is that the atmosphere may swiftly adapt to localized solar heating conditions. Furthermore, Mars is devoid of oceans, which exacerbates temperature variations. The surface displays considerable elevation differences. The internal atmosphere is overly heated due to particulate matter, and considerable atmospheric buildup transpires at the poles, dissipating with each season. The near-surface breezes at the Viking and Pathfinder landing sites demonstrated similar patterns and were primarily gentle. The mean velocities were often under 2 meters per second, 4.5 miles per hour, with gusts reaching 40 meters per second, 90 miles per hour. Further observations have provided more insights into surface winds, including wind-blown dust streaks, dune field forms, and diverse cloud patterns. Global circulation models, accounting for all known elements affecting atmospheric behavior, suggest that seasonal variations will greatly impact Martian winds. The borders of the polar caps see considerable temperature fluctuations over the surface during fall and winter. Intense jet streams with eastward velocities of 100 meters per second, 225 miles per hour, form at high latitudes in winter. Circulation is diminished when calm winds are prevalent during spring and autumn. Unlike Earth, a significant north-south circulation on Mars enables atmospheric transfer between the winter and summer poles. Significant wave movements and instabilities suggest that the overall circulation pattern is unstable. The pressure and wind measurements from the Viking lander sites clearly demonstrate a uniform pattern of rotating high and low pressure systems. Minor motions and oscillations are common and affected by solar activity and surface topography. At the Viking and Pathfinder landing sites, wind direction and velocity vary daily due to the Sun's location and the local topography. Turbulence is essential for lifting and maintaining the dust in the Martian atmosphere. Dust storms generally arise in preferred southern hemisphere regions during the spring and summer months. The activity is initially confined and powerful, inexplicably sending significant particles into the atmosphere. Upon attaining a critical mass, the dust storm intensifies rapidly, with powerful winds dispersing the dust worldwide. Over a few days, the storm obscures the whole surface, reducing visibility to less than 5% of normal levels. The intensification process is transient, as air clarity swiftly returns to normalcy, typically within a few weeks. Spacecraft photos and altimetry have unequivocally delineated the Martian landscape. Almost the whole planet has been imaged from orbit at a resolution of 20 meters, 66 feet, with certain areas recorded at resolutions as precise as 20 centimeters, 8 inches. The laser altimeter aboard Mars Global Surveyor has documented surface heights for the whole planet, averaged over a 300-meter diameter circle, with a vertical precision of 1 meter. We have produced maps illustrating topography, geology, temperature, mineral distributions, and additional data. Subsequently to Mariner 9, the prime meridian on Mars, comparable to the Greenwich meridian on Earth, was defined to pass through a small crater named Airy 0 within the larger crater. Scientists quantified longitude in degrees, advancing westward from this meridian and worldwide. Consequently, some scientists preferred a coordinate system where longitude advances eastward from the prime meridian. As a result, scientists published maps of Mars employing one or both of these coordinate systems. Despite its small size, Mars has significantly greater topographical relief than Earth. The deepest point on Earth, situated in the Hellas Impact Basin, is 8 kilometers, 5 miles, below the reference level. The summit of Olympus Mons, the highest volcano, is 21 kilometers, 13 miles, above the reference level. The height range is thus 29 kilometers, 18 miles, compared to around 20 kilometers, 12.4 miles, on Earth, namely from the base of the Mariana Trench to the summit of Mount Everest. In the lack of oceans on Mars, a reference elevation level was constructed using criteria distinct from sea level. In the early 1970s, the altitude associated with an atmospheric pressure of 6.1 millibars, about 0.06 of sea level pressure on Earth, was designated as the reference point. Upon acquiring upgraded elevation data from the Mars Global Surveyor, we designated the planet's average radius of 3,389.51 kilometers, 2,106.14 miles, as a more precise reference. The contrast between the southern and northern hemispheres is a significant characteristic of the Martian terrain. The southern hemisphere is predominantly elevated and heavily cratered, resembling the battered highlands of the Moon. Most of the northern hemisphere is defined by low height and a paucity of craters. The difference in average elevation between the two hemispheres is roughly 6 kilometers, 3.7 miles. The topographic boundary between the hemispheres is not straight to the equator. Instead, it roughly delineates a wide circle tilted at around 30 degrees. In some regions, the barrier is extensive and uneven. In others, it consists of sheer cliffs. Substantial erosion on Mars is noted along the perimeter. The observable landforms include outflow channels, collapsed regions termed chaotic terrain, and a perplexing combination of valleys and ridges referred to as fretted terrain. The Tharsis Rise delineates the boundary in the Western Hemisphere, a massive volcanic formation with a diameter of 4,000 kilometers, 2,500 miles, and an elevation of 8 kilometers, 5 miles, above the reference level at its core. It ascends 12 kilometers, 7.5 miles, above the northern plains and surpasses 2 kilometers, 1.2 miles, above the neighboring cratered southern highlands. The most substantial volcanoes on the planet are situated on or adjacent to the Tharsis Rise. Landforms produced by plate tectonics are completely non-existent in both hemispheres. No oceanic trenches, huge linear mountain ranges like the Andes, or a global network of interconnecting ridges are present. The hemisphere dichotomy probably resulted from a substantial asteroid impact on Mars in its formative period. The resulting impact crater in the northern hemisphere measures around 8,500 by 10,700 kilometers, 5,300 by 6,600 miles. The striking object would have surpassed 2,000 kilometers, 1,200 miles, in diameter. Gravity measurements from Mars Global Surveyor reveal that the Martian crust is considerably thicker under the southern highlands than the northern plains. The prevalence of extensive craters in the southern highlands suggests a significant age for the surface. Researchers examining planetary bodies have discovered from lunar samples obtained during the Apollo missions that the frequency of substantial asteroid impacts on the Moon was significantly elevated shortly after its formation 4.5 billion years ago, declining rapidly between 3.8 billion and 3.5 billion years ago. The Moon's surface was heavily cratered before its descent, but those created afterward were comparatively less. Mars underwent a similar cratering history. Thus, the southern highlands originated more than 3.5 billion years ago. The southern topography exhibits several crater forms, including extensive impact basins, massive partially filled craters with shallow flat floors and worn rims, smaller immaculate bowl-shaped craters resembling those on the Moon, and rampart and pedestal craters. The Hellas impact basin on Mars is the largest of its type, with a depth of 8 kilometers, 5 miles, and a diameter of nearly 7,000 kilometers, 4,350 miles, including the vast raised ring surrounding the depression. Crater formations measuring tens to hundreds of kilometers are markedly eroded, while smaller craters on the more recent plains display negligible erosion. The difference indicates that erosion rates were markedly increased on early Mars. This signifies that early Mars's climate significantly differed from most of its historical conditions. Numerous Martian craters display unique attributes in contrast to those on the Moon. A rampart crater is defined by ejecta lobes, material released from the crater and its vicinity, encircled by a low ridge or rampart. The ejecta appeared to move across the landscape, indicating it had a mud-like substance. Some experts have postulated that the mud is derived from impact debris and subterranean water. The ejected material encircling a pedestal crater forms a steep-sided platform, or pedestal, containing the crater within its boundaries. The pedestal appears to have developed as wind eroded the surface layer of the surrounding region, but the section covered by the overlaying ejecta remained intact. High-resolution Viking photographs revealed another characteristic of the ancient southern landscape: the extensive presence of networks of tiny valleys resembling terrestrial drainage systems created by running water. Examples include Nirgal Vallis, located in the southern hemisphere north of the Argia impact basin, and Nanedi Vallis, situated just north of the equator toward the eastern end of Valles Marineris. Researchers have suggested two possible reasons for their formation: surface runoff from precipitation or erosion, caused by groundwater drainage reaching the surface. In both cases, increased temperatures may have been essential for their formation. The Mars Global Surveyor mission disclosed small, recently formed gullies on steep inclines at high latitudes. These features closely mimic water-eroded gullies observed in Earth's desert terrains. Ice melting at the poles presumably initiated their formation, whereas periods of increased obliquity resulted in their deposition at lower latitudes. The plains display fewer impact craters than the southern highlands, suggesting their construction occurred after a decline in impact rates. The creation occurred roughly 3.8 to 3.5 billion years ago. The plains can be divided into two main regions: the volcanic plains of Tharsis, mostly created by lava flows, and the northern plains. The northern plains display negligible topographical diversity. They encompass all terrain within 30 degrees of the pole, excluding the adjacent layered terrains. The northern plains have many types of topography. The irregular landscape consists of numerous small hills mixed with level plains. The hills are remnants of an old cratered landscape, now predominantly concealed by more recent sedimentary deposits forming the plains. Many plains display a polygonal fracture pattern, similar to landforms in Earth's frozen areas. Certain surfaces display a unique thumbprint-like texture, possibly indicating the prior presence of stagnant ice. The origin of the low-lying northern plains is disputed. Lava comprises sections of the plains, similar to the Luna Maria. Certain experts propose that these regions were formerly occupied by oceanic bodies of water maintained by significant floods, and that the surface of the plains is composed of sedimentary layers. Spectrometers on orbiting spacecraft and the Mars exploration rovers have determined that the old highlands consist of distinct minerals compared to the younger lowlands. The rover Spirit landed on a basalt plain that may exemplify such terrains. The plains predominantly consist of typical basalts, featuring thin alteration rinds enriched in sulfur, chlorine, and various volatile elements. The interaction between the basalts and acid fog presumably led to the creation of the rinds. The rover navigated the ancient Columbia Hills, characterized by diverse geological structures. Most comprise basalts and impact breccias. However, some specimens display extensive alteration and are rich in sulfates and hydrated minerals. Soils mostly consisting of sulfates or silica are also present. Thermal volcanic fluids have permeated certain rocks, or increased surface temperatures have weathered them. This assemblage of rocks and soils may indicate the highlands in general. The results from orbit present a similar account. The plains primarily contain unaltered basaltic minerals such as olivine and pyroxene. In contrast, alteration minerals like clays are widespread throughout the old cratered terrain. The results indicate that surface conditions substantially changed around 3.7 billion years ago. Before that epoch, warm and humid circumstances dominated, causing substantial rock alteration. Thereafter, these conditions became rare, leading to negligible rock alteration. The dominating ancient cratered terrain is traversed by networks of desert valleys, primarily ranging from 1 to 2 kilometers in width and extending up to 2,000 kilometers, 1,200 miles, in length. Structurally, They are analogous to terrestrial river systems. Flowing water likely shaped the valleys by progressive erosion. Many local lowlands exhibit an entrance valley and an outflow valley, indicating that the area once contained a lake. Layered deposits, presumably generated in lacustrine environments, generally underlie these areas, and deltas frequently occur where valleys intersect with the lowlands. Valley networks are rare, but not completely missing in the younger, less extensively cratered areas. Identifying the valleys in the 1970s was unforeseen due to the difficulties posed by surface water under prevailing conditions. Their pervasive presence in the highly cratered terrain indicates that early Martian conditions were considerably warmer and more humid than present ones. Many areas of the Martian surface have massive flood channels known as outflow channels. The canals substantially surpass the valley networks in dimensions, generally measuring tens of kilometers in width and stretching hundreds of kilometers in length. Most rise from debris-filled depressions and move downslope into the northern plains or the Hellas Basin to the south. Several significant drains originate from the south and west, converging into Chrysa Planitia. These are authentic channels, once completely filled with flowing water, unlike most river valleys that have never been totally inhabited and possess a narrower river channel. The peak discharges of the floods that created the larger outflow channels are believed to have been 100 to 1,000 times greater than the peak discharge of the Mississippi River. Extraordinarily monumental occurrences. Some floods appear to have been caused by the catastrophic release of water from lakes. Others are formed by explosive groundwater eruptions. The outflow channels are more recent than the valley networks and likely developed under conditions like today. The recent identification of youthful outflow channels suggests they may originate from groundwater eruptions beneath the kilometer-thick permafrost. Near the equator, around 70 degrees west longitude, is a network of extensive interconnected canyons referred to as valles marineris. Individual canyons measure roughly 200 kilometers, 125 miles, in width. Numerous canyons merge in the system's center, forming a depression with a diameter of 600 kilometers, 375 miles, and depths reaching 9 kilometers, 5.6 miles. Approximately 5 times deeper than the Grand Canyon, the entire system spans 4,000 kilometers, 2,500 miles, constituting almost 20% of Mars's radius, nearly comparable to the breadth of the United States. Multiple sites within the canyons display concentrated sulfate-rich sedimentary formations, suggesting the prior existence of lakes in the canyons. Some lakes may have experienced catastrophic drainage to the east, leading to vast outflow canals that originate near the eastern ends of the canyons. Erosion sculpted the Grand Canyon, whereas faulting predominantly formed the valles marineris, with further erosion enlarging them. The valles marineris canyons terminate in the west at the summit of the Tharsis Rise, a substantial elevation on Mars's surface that spans over 8,000 kilometers in width and reaches a height of 8 kilometers at its apex. At the apex of the elevation are 3 of the planet's largest volcanoes, Ascraeus Mons, Arsia Mons, and Pavonis Mons, reaching altitudes of 18, 17, and 14 kilometers, 11.2, 10.5, and 8.7 miles, respectively, above the average radius. Situated in the northwest, Olympus Mons is the highest volcano in the world. Alba Patera, the most extensive volcano in the region, is situated to the north. It extends 2,000 kilometers, 1,250 miles, in breadth, yet only reaches a height of 7 kilometers, 4.3 miles. Among these massive formations are several lesser volcanoes and lava plains. Tharsis is a vast assemblage of volcanic rock, primarily produced 3.7 billion years ago, and has continued to be a center of volcanic activity since then. The rising tharsis has caused strains and deformation in the crust. This phenomenon is exemplified by the vast network of fractures emanating from tharsis and the compressional ridges surrounding the uplift. The radial faulting, encircling tharsis, has enabled forming the Valles Marineris system. A supplementary volcanic elevation is situated in the northern region of Elysium, at roughly 215 degrees west longitude. The Elysium rise is considerably smaller than tharsis, with a diameter of only 2,000 kilometers and an elevation of 6 kilometers, 3.7 miles. It is also the site of several volcanoes. Olympus Mons, the most colossal volcano in the solar system, is the apex of Mars. Situated at 19 degrees north, 133 degrees west, Olympus Mons has a central edifice approximately 22 kilometers tall and 700 kilometers, 400 miles wide. A vertical cliff ascends 10 kilometers, 6 miles, along its perimeter, exceeding the adjacent landscape. The top comprises a caldera about 85 kilometers, 53 miles, in diameter, along with other crossing craters. Mauna Loa, the largest volcano in Hawaii, measures 120 kilometers, 75 miles, at its widest point and rises 9 kilometers, 5.6 miles, above the ocean floor. Olympus Mons features broad, moderately inclined slopes, with numerous lava flows and channels, indicating that it is a shield volcano characterized by predominantly basaltic lava that flows with ease. The durability of the Martian crust and a prolonged accumulation period, possibly beyond 1 billion years, have resulted in its considerable magnitude. Each pole comprises a layered accumulation of water-ice-laden sediments around 3 kilometers thick, and only a few tens of millions of years old. The stratification is evident at the sediment margins and valleys extending from the poles. During winter, carbon dioxide frost encases the sediments, whereas summer exposes them. They extend southerly from the North Pole to 80 degrees latitude. Their limits are less clearly defined in the South Pole. However, they extend farther from the pole than in the northern area. The stratification is believed to result from variations in the quantities of dust and ice, perhaps induced by alterations in the tilt of the rotational axis. At increased obliquities, water ice is ejected from the poles, potentially leading to the total eradication of the remnant water ice caps and ice accumulation at lower latitudes. At minimal obliquity, the polar ice caps attain their maximum extent. Fluctuations in obliquity additionally affect the frequency of dust storms and dust accumulation near the poles. New deposits have emerged following the previous period of heightened obliquity, which degraded the earlier layers. A notable characteristic of the sediments at the North Pole is their surroundings, which may rest on a vast dune area rich in the sulfate mineral gypsum. At latitudes above 40 degrees, ground ice is permanently stable, at depths of around 1 meter or more, as temperatures do not exceed the frost point. At latitudes surpassing 60 degrees, the ice is sufficiently shallow to be discernible from orbit. The Phoenix lander identified an ice subsurface around 68 degrees north latitude. Multiple surface characteristics indicate significant ground ice exists at latitudes over 40 degrees. This encompasses terrain fragmented into polygons such as regions with perennial frost, alongside a general substrate softening likely induced by the mobilization of near-surface minerals facilitated by ice. The most prominent characteristic of the 40 to 60 degree latitude bands related to ice is the presence of debris aprons at the base of most steep slopes. Debris from the slopes appears to have traversed several kilometers, and ground-penetrating radar reveals that the aprons contain substantial quantities of ice. During periods of increased obliquity, ice transferred from the poles accumulated at lower latitudes, perhaps leading to the creation of glaciers. Atmospheric circulation models indicate that the Tharsis volcano's western slopes and the Hellas Basin's northeastern region are optimal locations for ice formation during these periods. All these locations display numerous flow characteristics and moraine-like landforms, signifying the historical existence of glaciers. The northern polar region also contains the greatest sand dunes on Mars. The dunes in the northern area of Vastitas Borealis form a band that almost completely surrounds the North Polar remnant cap. The presence of sand interlayers and seasonal carbon dioxide snow in specific areas indicates that the dunes have seasonal activity. Many surface features on Mars are notable for their distinctive topography. Earth probes have performed comprehensive investigations of distant celestial bodies. The following subsections clarify specific aspects in further depth. Chryse Planitia is a flat, low-lying region in the Northern Hemisphere, selected as a landing location for the United States. Viking 1 and Mars Pathfinder spacecraft. The Viking 1 lander touched down at 22.48 degrees north, 47.97 degrees west on July 20, 1976. The study revealed that Chryse Planitia is a wavy, boulder-strewn plain characterized by scattered dusty dunes and visible bedrock formations. Mars Pathfinder met a similar terrain upon landing at 19 degrees 33 minutes north, 33 degrees 22 minutes west, on July 4, 1997. The surface rocks of Chryse Planitia are believed to be weathered relics of basaltic lavas brought to the site by substantial floods during Mars's early history. The Viking and Pathfinder landers' instruments examined the dusty soil and established that silicon dioxide, SiO2, and various oxides comprised the predominant materials by weight. 46% silica, SiO2, 18% iron, Fe2O3, 8% aluminum, Al2O3, 7% magnesium, MgO, 6% calcium, CaO, 5.4% sulfur, SO3, 2% sodium, Na2O, and 0.3% potassium, K2O. This composition corresponds to igneous rocks, formed from magmas interacting with underlying ice. The rocks subsequently underwent weathering and leaching, resulting in surfaces stained with red iron oxide minerals, and an increased sulfate content in the soil, potentially including carbonates. The vast impact basin Hellas in Mars' southern hemisphere is the planet's most significant recognizable impact feature. Situated at roughly 40 degrees south, 290 degrees west, Hellas measures over 7,000 kilometers, 4,400 miles, in diameter, including a vast elevated rim surrounding the depression, with a depth of 8 kilometers, 5 miles. The surface, embellished with slightly weathered sand, signifies the nadir on Mars. A collision with an asteroid presumably created the basin during Mars's early history, shortly after the planet's birth. Nergal Vallis is a complex branching valley north of the Argyre impact basin, approximately around 28 degrees south, 42 degrees west. It extends over 400 kilometers, 250 miles, in length, and approximately 5 kilometers, 3 miles, in width. The name derives from the Babylonian nickname for Mars. Initially detected in photos from the Mariner 9 spacecraft, the valley exhibits numerous tributaries and appears to have been formed by the progressive erosion caused by flowing water. The water source, whether from precipitation, snowmelt, or groundwater intrusion, is disputed. The genesis of the gullies on the valley's steep walls, as documented by the Mars Global Surveyor satellite, remains a subject of debate. Some experts claim that recent groundwater seepage is the origin of their development, while others argue that dry or gas-lubricated debris flows are responsible. Syrtis Major is a significant dark feature situated at around 290 degrees west and 10 degrees north, extending roughly 1,500 kilometers northward from the equator and measuring 1,000 kilometers, 620 miles, in breadth from west to east. Christian Huygens spotted it as early as 1659, as demonstrated by a drawing of Mars from that year. It is an extensive regional slope, spanning from north to south, falling 4 kilometers, 2.5 miles, from its western boundary, area, to its eastern edge, Isidis. Syrtis Major has been rigorously examined for over a century because of its seasonal and long-term fluctuations, especially along its eastern margin. It was once considered a superficial sea. Ultimately, scientists attributed its unpredictability to vegetation. Detailed photos and data supplied by the US, the Mariner and Viking planetary probes of the 1960s and 1970s, enabled researchers to determine that the changes are due to wind carrying sand and dust over the surface. In the early 1980s, comprehensive topographical maps derived from spectroscopic and radar investigations conducted on Earth, and images captured by space probes revealed that Syrtis Major exhibits a notable elevation of 6 kilometers near 310 degrees west. The US Viking 2 planetary probe selected Utopia Planitia, a northern lava plain, as its landing site. The images transmitted by the Viking 2 lander, which landed at 47.97 degrees north, 225.74 degrees west on September 3, 1976, depicted a plain strewn with boulders that superficially resembled the Viking 1 landing site in Chrysi Planitia. The lander's examinations of soil samples reveal that the soil compositions at the two locations are almost identical. This is likely attributable to the convergence of wind-driven dust from diverse areas of the Earth. The Utopia plain differs from the Chrysa region due to its system of shallow troughs, possibly associated with ice wedge processes stemming from permafrost. The lander observed vesicular boulders at the Utopia location. These stones exhibit microscopic gas-formed cavities indicative of their volcanic origin. The boulders may have originated from local lava flows or debris ejected by the adjacent Mai impact crater. Images from the Viking 2 lander revealed a tenuous covering of white ground frost, composed of water ice that persisted for approximately 100 days throughout the two documented winters on Mars. Carbon dioxide likely initiates frost formation, which subsequently melts under sunshine, leaving the water component alone. Vastitas Borealis is a largely level lowland plain surrounding the northern pole of Mars, extending southward to roughly latitude 50 degrees. The aircraft is situated 4 to 5 kilometers, 2.5 to 3 miles, beneath the planet's average radius. In some areas, it is characterized by several low hills of rather regular dimensions, likely relics of a primordial cratered terrain, now predominantly concealed by more recent sedimentation. It has a polygonal fracture pattern similar to that found in permafrost areas on Earth. A vast dune field encircles the northern portion of the plain, almost completely enclosing the pole. The origin of Vastitas Borealis is still disputed. Spacecraft imagery has disclosed that extensive flood channels, termed outflow channels, once transported significant volumes of water into this region from the higher Topography to the south. Certain scientists suggest that the plain's uniform, nearly level topography is the product of sediments deposited by an ocean that arose from floodwaters, which submerged a substantial area of the northern plains. They employ features akin to shorelines and terraces surrounding low hills as proof. Some argue that the flat surface and linear characteristics result from marine processes, suggesting that the floodwater covered only a small northern plains area. The interior of Mars is little comprehended. Researchers investigating planets have been unable to effectively employ spacecraft for a seismic experiment that would provide direct insights into their structure, necessitating reliance on inferences. Mars's moment of inertia suggests the presence of a central core with a radius ranging from 1,300 to 2,000 kilometers, 800 to 1,200 miles. Mars evolved into a metal-rich core and silicate mantle following the planetary accretion period 4.5 billion years ago, as isotopic meteorite data indicates. The planet has no detectable magnetic field, indicating a current lack of convection in the core. Significant regions of magnetized rock have been discovered in the primordial landscape, suggesting that early Mars had a magnetic field, which later dissipated as the planet cooled and its core consolidated. Martian meteorites suggest that the core may have a larger sulfur content than Earth's core, whereas the mantle may exhibit a greater concentration of iron. Mars is probably volcanically active, though at a low intensity. Some Martian meteorites, all of volcanic origin, display ages as recent as several 100 million years. But certain volcanic terrains on the planet are so sparsely cratered that they must be only tens of millions of years old. As a result, Mars demonstrated volcanic activity in the geologically recent past, suggesting that its mantle is thermally raised and undergoing localized melting. The gravitational field of Mars markedly contrasts with that of Earth. Isostatic compensation refers to the inclination of subsurface masses inside the Earth's crust to equilibrate excess or deficient masses. This transpires as a result of significant mountains and deep oceans, respectively. The gravitational force on Earth is the same at high altitudes as it is above the seas. This pertains to Mars's oldest landscapes, encompassing the Hellas Basin and the Southern Highlands. Nonetheless, the younger terrains, such as the Tharsis and Elysium domes, display barely incomplete compensation. Gravity anomalies, particularly gravity highs, define both places, as the dome's significant mass considerably increases the measured gravitational force. These zones resemble the mascons delineated and mapped on Earth's moon. The Southern Highlands possess a gravitational force comparable to the low-lying northern plains. This indicates that the Southern Highlands are underpinned by a thicker crust composed of less dense material than the underlying mantle. The thickness of Mars' crust is estimated to vary from approximately 3 kilometers beneath the Acidus Impact Basin, located north of the equator and east of Syrtis Major, to over 90 kilometers near the southernmost region of the Tharsis Rise. Researchers have detected more than 50 meteorites that originated from Mars. Concerns about their origin arose when meteorites resembling volcanic materials were found to be roughly 1.3 billion years old, unlike the 4.5 billion years typical of all other meteorites. These rocks likely originated from a geologically active source in the relatively recent past, with Mars as the most probable choice. The rocks have similar ratios of oxygen isotopes, significantly different from those present in terrestrial rocks, lunar rocks, and other meteorites. The origin on Mars was conclusively established when multiple specimens were discovered to have trapped gases with a composition identical to that of the Martian atmosphere, as analyzed by the Viking landers. Researchers assert that substantial impacts dislodged the rocks from the Martian surface. They subsequently entered solar orbit for several million years before descending to Earth. The mid-1990s allegations concerning the discovery of evidence for ancient microscopic life in the meteorite ALH 84001 have been received with suspicion by the scientific community. Limited understanding was attained concerning Mars's two moons, Phobos and Deimos, after their discovery by American astronomer Asaph Hall in 1877, until orbital spacecraft studied them a century later. Viking 1 neared Phobos to within 100 kilometers, but Viking 2 approached Deimos within 30 kilometers, 20 miles. The Viking spacecraft disclosed that both moons are unevenly shaped rock fragments, about ellipsoidal in shape. Phobos and Deimos are not visible from all locations on Earth due to their small size, proximity to Mars, and near equatorial orbits. Phobos is the bigger inner moon of Mars. It is a small, irregularly shaped stony body with a cratered and grooved surface. Phobos, a roughly ellipsoidal entity, possesses a maximum diameter of 26.6 kilometers, 16.5 miles, It executes one circle about Mars every 7 hours and 39 minutes at an exceptionally close average distance of 9,378 kilometers, 5,827 miles, adhering to a nearly circular course inclined merely 1 degree off the planet's equatorial plane. In the absence of intrinsic strength, gravitational tidal forces would lead Phobos to disintegrate due to its proximity to Mars. Phobos moves across the Martian sky from west to east because its orbital period is shorter than Mars' rotational period of 24 hours and 37 minutes. The elongated axis of Phobos consistently aligns with Mars. Akin to Earth's moon, it has a rotating period that corresponds with its orbital period, presenting a constant face to the planet. Phobos's heavily cratered surface is covered with a dark grey regolith that reflects approximately 6% of the incident light, roughly half that of the Moon's surface. This fact, coupled with the satellite's low average density, 1.9 grams per cubic centimeter, or 1.1 ounces per cubic inch, aligns with the composition of carbonaceous chondrite meteorites. This suggests that Phobos may be a captive asteroid-like object. Prominent linear grooves extend throughout a considerable surface area, typically measuring 100 meters in width and 20 meters in depth. Convincing evidence suggests their connection to the creation of the greatest crater on Phobos. The Stickney structure has a diameter of roughly 10 kilometers, 6 miles. Precise measurements of Phobos's position over the past century demonstrate that tidal forces from Mars are progressively pulling the spacecraft nearer to the planet. If this is the situation, it may affect Mars within the next 100 million years. Deimos is the lesser and more remote of Mars's 2 moons. The cratered surface of this irregularly shaped rock is covered with a thick coating of tiny particles. Deimos, somewhat ellipsoidal in shape, has a maximum dimension of around 15 kilometers, 9 miles. It orbits Mars every 30 hours and 18 minutes at an average distance of 23,459 kilometers, 14,577 miles, on a circular path within 2 degrees of Mars's equatorial plane. The satellite's longitudinal axis consistently aligns with Mars. Akin to Earth's moon, it has a rotating cycle corresponding to its orbital period, ensuring a fixed orientation toward the planet. Tidal pressures are inducing Deimos to recede from the Earth. Despite its negligible gravity, roughly 1,000th that of Earth, Deimos has retained significant amounts of fine regolith on its surface. The surface appears smooth due to the loose particles partially concealing its craters. The largest crater near the satellite's southern pole has a diameter of approximately 2.5 kilometers, 1.6 miles. The surface of Deimos is grey and extremely dark, with a reflectivity of only 7%, about half that of the Moon's surface. The satellite's low average density, below 2 grams per cubic centimeter, 1.16 ounces per cubic inch, suggests a carbonaceous nature, indicating that Deimos may be an asteroid-like object that was captured. Since the commencement of the space age, Mars has been a central subject of planetary exploration for 3 principal reasons. 1. It is the most Earth-like planet. 2. It is the planet most likely to have supported indigenous life, excluding Earth. And 3. It is expected to be the first extraterrestrial planet visited by humans. Between 1960 and 1980, Mars exploration was a principal objective of the US and Soviet space programs. US spacecraft successfully executed flybys of Mars, Mariners 4, 6, and 7, orbited the planet, Mariner 9 and Vikings 1 and 2, and dropped lander modules on the surface, Vikings 1 and 2. 3 Soviet spacecraft, Mars 2, 3, and 5, investigated Mars, with 2 achieving successful landings on its surface. Mars 3 was the first spacecraft to accomplish a soft landing of an instrumented capsule on the planet on December 2nd, 1971. It landed during a worldwide dust storm and sent data for around 20 seconds. From November 1971 to October 1972, Mariner 9, the first spacecraft to orbit another planet, operated near Mars. It produced a varied collection of spectroscopic, radio propagation, and photographic data. Approximately 7,330 images, encompassing almost 80% of the surface, depicted a history of significant volcanic eruptions, ancient water erosion, and the alteration of extensive surface areas by internal geological forces. The principal objective of the Viking missions was the search for alien life. No definitive evidence of life was discovered. Nonetheless, the various sensors aboard the 2 orbiters and 2 landers provided substantial information regarding the geology and meteorological conditions on Mars and the physics and chemistry of the upper atmosphere. The Vikings 1 and 2 spacecraft were launched into orbit in June and August of 1976, respectively. The lander modules descended from orbit to the Earth after locating suitable places. Viking 1 landed in Chris Planitia on July 20, 1976, whilst Viking 2 touched down 6,500 kilometers, 4,000 miles away in Utopia Planitia on September 3, 1976. In 1988, Soviet scientists launched the Phobos 1 and 2 spacecraft to orbit Mars and performed incremental flyby investigations of its 2 moons. Phobos 1 failed during its year-long mission, whereas Phobos 2 successfully reached Mars in early 1989 and sent several days of observations of the planet and Phobos before experiencing a malfunction. In the 1990s, after several unsuccessful US spacecraft missions to Mars, Mars Pathfinder successfully landed in Chrysoplanitia on July 4, 1997, and placed a robotic-wheeled rover called Sojourner on the Martian surface. Mars Global Surveyor reached Mars in September 1997 and systematically studied the planet's characteristics from orbit for several years, beginning in March 1999. These included Mars's gravitational and magnetic fields, surface topography, and mineral composition. The spacecraft's cameras obtained wide-angle, high-quality surface photos with a resolution of up to 1.5 meters, 5 feet. Mars Odyssey successfully achieved Mars orbit in October 2001 and initiated the mapping of numerous aspects, including the chemical composition of the surface, the distribution of near-surface ice, and the physical characteristics of near-surface materials. Numerous spacecraft approached Mars in late 2003 and early 2004, with diverse outcomes. Nozomi, initiated by Japan in 1998 on a leisurely trajectory, was the first to reach the neighborhood of the planet. However, problems prevented its entrance into Mars's orbit. The European Space Agency launched the Mars Express mission in mid-2003, beginning a 6-month journey to the Red Planet. Equipped with instruments to analyze the atmosphere, surface and subsurface, it entered Mars orbit on December 25th. However, its lander, Beagle 2, designed to investigate the rocks and soil for evidence of past or present life, failed to establish radio contact after presumably descending to the Martian surface on the same day. Upon its arrival, the Mars Express orbiter detected substantial quantities of water ice and carbon dioxide ice at the South Pole, and confirmed that the residual cap from the southern summer, like the northern cap, contains permanently frozen water. It also detected significant sulfur-rich concentrations in Valles Marineris and clay minerals in the highly cratered areas. In mid-2003, the United States also initiated action. The Mars Exploration Rover mission comprised 2 robotic landers, Spirit and Opportunity. Spirit alighted in Gusev Crater, 15 degrees south, 175 degrees east, on January 3rd, 2004. 3 weeks later, on January 24th, Opportunity landed at Meridiani Planum, 2 degrees south, 6 degrees west, in the planet's opposite hemisphere. The 6-wheeled rovers, equipped with cameras and various instruments like a microscopic imager and a rock-grinding tool, analyzed the rocks, soil, and dust in their landing areas, chosen for their evident past involvement with water on Mars. Both rovers revealed evidence of past water. Specifically, Opportunity identified rocks that appeared to have developed along the shoreline of an ancient saline body of water. In 2005, the United States launched the Mars Reconnaissance Orbiter, outfitted with an imaging system that boasts a resolution of 20 centimeters or 8 inches, a spectrometer for surface composition analysis, and ground-penetrating radar. The spectrometer indicated that the old cratered landscapes are abundant in clay minerals and other alteration products, suggestive of a warm, remote period. The radar identified glaciers and evaluated the ice thickness at the poles. In 2008, the US spacecraft Phoenix alighted in the northern polar zone of Mars. Phoenix conducted a tiny chemical laboratory to examine the Arctic soil, where it identified water ice beneath the Martian surface. Since the advent of telescopic studies of Mars, humanity has conjectured about the possibility of life originating there and its potential attributes. Initial observers primarily focused on intelligent life. However, the present emphasis is on the origins of life, microbial communities, and the limitations on their survival. Views on the possibility of life on Mars have varied considerably in recent decades. In the 1960s, a notion emerged suggesting that astronomical observations could have a biological origin. This resulted in the deployment of Mariner 9 in 1972 to monitor alterations on Mars's surface and the subsequent landing of the Viking landers in 1975. The Viking spacecraft was equipped with advanced experiments to discover metabolism and organic compounds. The adverse results of these trials fostered considerable pessimism about the potential for life, continuing throughout the 1980s. However, several factors subsequently cultivated a more favorable viewpoint. Scientists have now established that life can endure under a broader range of environments than previously believed. For instance, it may inhabit deep-sea vents with temperatures exceeding 1,000 degrees Celsius, 1,800 degrees Fahrenheit, basaltic rocks in subterranean depths, and very saline and acidic conditions. The second discovery indicates that life on Earth originated rapidly, possibly even before the conclusion of the massive bombardment. This implies that the emergence of life is not exceedingly improbable, provided that the appropriate conditions are satisfied. There is growing evidence that early Martian circumstances, coinciding with the development of life on Earth, were analogous to those on Earth. A fourth factor is the recognition that Earth and Mars exchange materials. Notwithstanding the difficulties in differentiating Martian rocks from terrestrial counterparts, Earth has identified over 50 specimens. Conveying terrestrial rocks to Mars presents greater challenges. During the heavy bombardment epoch, when life may have originated on Earth, and Martian circumstances were analogous to Earth's, terrestrial fragments could have been carried to Mars. Thus, life evolved autonomously on Mars, or was transmitted from Earth. In 1996, the scientific community was astonished when researchers presented signs of life within a Martian meteorite. To validate their conclusion, they listed: the electron microscope images depict entities akin to bacteria and reveal the presence of hydrocarbons. 3. Mineral assemblages that did not develop under circumstances of chemical equilibrium. The announcement sparked a vigorous scientific debate about the validity of the claims. The prevailing scientific consensus asserts that all observations had reasonable abiological explanations, rendering the claims likely invalid. Despite this setback, the principal motivation of the Mars exploration mission continues to be the search for life. The main focus has been on identifying evidence of heated circumstances that would enable the presence of liquid water due to its essential role in life. Compelling evidence now exists for these conditions, particularly during the formative period of Mars. The exploration emphasis may transition towards acquiring more direct evidence, such as organic remnants and isotopic markers. The most effective approach is to seek fossil remnants from Mars's history when its conditions were similar to Earth's. Discussions over Martian meteorites and disputes concerning primordial life on Earth illustrate the difficulty in obtaining compelling evidence of microbial existence in fossils. Alternatively, one can argue that the most effective strategy is to investigate modern life in environments such as warm volcanic regions, positing that if life had emerged on Mars, it would have persisted through harsh conditions.